Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the universe slows to a gentler pace, and even the strangest corners of space become a little softer around the edges. Tonight, we're travelling farther than almost any human being naturally can. Far beyond our galaxy, beyond familiar stars, beyond the great glowing cities of the cosmos, to meet something that by all reasonable accounts should not exist at all. Its name is J0313-1806, which admittedly sounds less like a cosmic monster and more like a password you forget immediately after creating it. But hidden behind that rather unfriendly catalogue name is one of the most baffling objects astronomers have ever discovered. A black hole so enormous, so ancient and so unexpectedly mature that it forced scientists to pause, stare at the data, and quietly reconsider whether the early universe was behaving itself at all. Because this black hole appeared far too early. It existed when the universe itself was still extremely young. Young enough that, according to many of our standard models of cosmic growth, there simply should not have been enough time for something this massive to form. And yet, there it was. Like arriving at a toddler's birthday party only to discover one guest has already retired, owns 3 vacation homes, and is asking whether anyone has checked the stock market lately. Before we begin untangling this impossible mystery together, though, I'd love to ask something simple. Where in the world are you listening from tonight? And what time is it in your little corner of Earth right now? Maybe it's late evening, and the room has finally gone quiet after a long day. Maybe rain is tapping softly against the windows. Maybe the rest of the house is asleep already, and you're tucked beneath blankets while distant stars carry on overhead, completely unaware of tomorrow's emails. Or perhaps it's early morning somewhere, and the sky's only beginning to brighten. Either way, I'm very glad you're here. And if you find this journey calming, cozy, or simply a pleasant place to let your thoughts drift for a while, I'd be ever so grateful if you liked the video and subscribed. It helps this sleepy little corner of science reach more fellow travellers looking for a peaceful landing place at the end of the day. Now then, settle in comfortably, loosen the grip of the day for a little while, and let's move slowly into the darkness together. Because tonight's story begins in a universe that was barely awake. When most people picture the early universe, they imagine chaos, blazing energy, violent explosions, matter racing in every direction, a newborn cosmos still trying to decide what exactly it wanted to become. And to be fair, that picture is not entirely wrong. The early universe was extraordinarily intense, temperatures were unimaginably high, radiation flooded space, tiny fluctuations in matter were beginning the long process of becoming galaxies, stars, planets, and eventually curious humans lying in bed listening to documentaries about black holes instead of going to sleep at a reasonable hour. But despite all that activity, the infant universe also had limits. There are certain things that simply take time. Galaxies need time to grow, stars need time to form, heavy elements need time to cook inside stellar furnaces. Even black holes, those famously hungry cosmic vacuum cleaners, are generally expected to grow gradually over enormous spans of time. At least, that's what astronomers thought. To understand why J0313-1806 is such a problem, we first need to talk about black holes themselves. Not the dramatic movie versions that swallow entire galaxies every afternoon before tea, but the real ones. The quieter, stranger, scientifically inconvenient ones. Most black holes begin with stars. Massive stars live surprisingly short lives. They burn through their fuel quickly, shining brilliantly for millions of years before eventually collapsing under their own gravity. When that happens, the core caves inward so violently that matter is compressed beyond ordinary understanding. If enough mass remains, a black hole is born. Usually these stellar black holes start relatively modestly, perhaps a few times the mass of our Sun. Large by human standards, certainly, but still manageable on the cosmic scale. Then comes the feeding. Black holes grow by consuming material around them. Gas falls inward. dust spirals closer. Occasionally entire stars wander too near and are torn apart in catastrophically unpleasant ways. Very slowly, over millions or billions of years, some black holes become truly enormous. At the centres of galaxies, including our own Milky Way, reside supermassive black holes. These giants can contain millions or even billions of times the mass of the Sun. Sagittarius. A star, the black hole at the centre of our galaxy, weighs about 4 million solar masses, which sounds enormous until you meet the true monsters. Some black holes reach billions of solar masses. They become gravitational engines around which entire galaxies organise themselves. They shape star formation. They hurl radiation across space. They influence the architecture of the universe itself. But here's the important part. Even the biggest black holes are expected to require time to grow. A lot of time. Imagine trying to build Mount Everest one grain of sand at a time. Even if you work continuously, eventually someone will ask why you've only reached the height of a garden shed after several thousand years. The universe operates similarly. Growth has limits. Matter falls inward at measurable rates. Radiation pushes material away. There are natural bottlenecks that prevent black holes from feeding infinitely fast. Astronomers call one of these limits the Eddington limit, which is a wonderfully scientific phrase meaning, please calm down before your own radiation blows dinner away. As matter falls into a black hole, it heats up tremendously. That hot material emits radiation outward. Eventually, if feeding becomes too aggressive, the outward pressure from radiation begins pushing incoming gas away. It creates a kind of cosmic traffic jam. So under ordinary conditions, black holes cannot simply gorge themselves instantly into gigantic sizes. They grow steadily, gradually, patiently, which is why J0313-1806 caused such alarm. Because astronomers detected it at a time when the universe was only about 670 million years old. Now, 670 million years may sound like an absurdly long period to us. After all, human civilization struggles to remember passwords for more than a week. But cosmically speaking, 670 million years is incredibly early. The universe today is roughly 13.8 billion years old. So discovering an ultra-massive black hole at only 670 million years after the Big Bang is a bit like walking into a bakery 5 minutes after opening and discovering someone has already completed a 7-tier wedding cake, frosted it perfectly, and somehow also invented croissants. Scientists immediately realised something was deeply strange. J0313-1806 was not just big, it was catastrophically big. Estimates suggested the black hole possessed roughly 1.6 billion times the mass of the Sun. 1 billion. At an age when the cosmos itself was barely out of infancy. And worse still, it appeared to be feeding furiously. The surrounding quasar, the intensely bright region formed by superheated material spiralling inward, was one of the most luminous objects ever observed from that era. That meant the black hole was actively growing even larger. Astronomers suddenly faced an uncomfortable possibility. Maybe our understanding of early black hole formation was incomplete, or maybe wildly incomplete. You see, science often advances through small corrections, tiny adjustments, careful refinements. Occasionally, though, the universe decides subtlety is overrated and drops a giant impossible black hole directly onto your equations. J0313-1806 became one of those moments. Researchers began asking difficult questions. How did it form so quickly? What kind of seed created it? Did the first stars behave differently than expected? Were conditions in the young universe far more chaotic than our models suggest? Or perhaps most unsettling of all, are we missing some fundamental piece of cosmic physics entirely? Because if a black hole this large existed this early, then something in the story happened faster than it should have. Much faster. And the more astronomers studied these ancient quasars, the stranger things became. J0313-1806 was not completely alone. Other supermassive black holes had also been discovered in the early universe, though this one pushed the limits, especially hard. Like a cosmic overachiever determined to make every other black hole look unmotivated. The discovery hinted that enormous black holes may have appeared surprisingly early throughout cosmic history. That realization changes how scientists think about galaxy formation itself. For a long time, many researchers assumed galaxies formed first, gradually gathering matter until central black holes emerged and grew inside them. But now, another possibility entered the conversation. What if black holes came first? What if these giant gravitational anchors formed rapidly and helped organize the galaxies around them? It's a little like discovering the foundation of a city may have existed before the streets, and this is where our story begins to widen. Because J0313-1806 is not merely about one black hole, it is about the young universe itself. To look at this object is to stare backward through almost the entire history of time. The light reaching Earth from J0313-1806 began travelling toward us more than 13 billion years ago, long before Earth existed, long before the Sun formed, long before oceans, trees, dinosaurs, or sleepy YouTube documentaries. That ancient light crossed expanding space for billions upon billions of years just to arrive here, where modern telescopes could finally collect it. There's something wonderfully strange about that. The photons entering astronomical instruments today began their journey when the cosmos was still learning how to make galaxies, and somehow, hidden within that faint, ancient glow was evidence of a black hole that should not have had enough time to exist. Of course, the universe has a long tradition of ignoring human expectations. For centuries, we believed Earth stood motionless at the centre of everything. The universe politely disagreed. Later, we assumed galaxies were the entire cosmos. Then we discovered billions more. We imagined space was static until expansion appeared. We thought time flowed universally until Einstein informed us it bends and stretches like cosmic dough. Again and again, reality has demonstrated a remarkable willingness to be stranger than anticipated, and black holes themselves have always occupied a special category of scientific discomfort. They sit at the boundary between known physics and mystery. General relativity predicts them beautifully. Quantum mechanics struggles around them awkwardly. Information behaves strangely near them. Time distorts around them. Matter vanishes into them. Even now, despite decades of study, black holes remain deeply unsettling objects. Not because they are evil or destructive, but because they expose the limits of our understanding. J0313-1806 does this especially well. It forces astronomers to confront the possibility that the early universe was capable of building colossal structures far more efficiently than expected. Some researchers suspect the first stars may have been extraordinarily massive, producing enormous black hole seeds from the beginning. Others wonder whether giant clouds of gas collapsed directly into black holes without forming stars first. A few even explore more exotic possibilities involving dark matter or unusual conditions in the primordial universe. At the moment, no single explanation fully solves the puzzle, and honestly, that uncertainty is part of what makes science beautiful. The universe is not obligated to fit neatly inside human assumptions. Sometimes discovery means finding answers. Other times, it means discovering your questions were too small. Out beyond the visible edge of ordinary human experience, hidden in ancient light, J0313-1806 waits like a challenge written across space-time itself. An impossible object, a giant from the dawn of creation, a black hole that arrived too early, grew too fast, and now quietly asks astronomers whether they truly understand how the cosmos began at all. Long before Earth existed, before the Milky Way had fully assembled its familiar spiral shape, before our sun ignited and began warming an empty patch of cosmic dust, the universe passed through an era so strange and unfamiliar that it would hardly resemble a night sky at all. In fact, for a very long time, there may not have been a proper night sky anywhere. No stars, no galaxies, no glowing rivers of light stretched across darkness, no constellations for ancient civilizations to imagine into heroes, bears, hunters, or kitchen utensils. Just vastness. A growing universe slowly cooling after the violence of the Big Bang, filled mostly with darkness and scattered gas. And yet somehow, within that young and unfinished cosmos, the impossible black hole J0313-1806 was already beginning its rise. To appreciate how bizarre that truly is, we first need to understand what the universe actually looked like back then. Not the polished artist impressions with colourful nebulae and dramatic music swelling in the background, but the real, early universe. Quiet in some ways, chaotic in others. A place where the first structures had barely begun to emerge. Oddly enough, one of the biggest misconceptions about the Big Bang is the idea that it was an explosion in space. It wasn't. The Big Bang was space itself expanding. Everything began incredibly hot, incredibly dense, and incredibly compressed. Matter, energy, space, and time were all tangled together in conditions so extreme that our current physics struggles to describe them fully. Then expansion began, very rapidly. Within fractions of a second, the universe ballooned outward in a process called inflation. Tiny quantum fluctuations stretched across enormous distances. These little irregularities would later become the seeds of galaxies and clusters and black holes. Which is rather remarkable when you think about it. Every galaxy, every star, every sleepy person drinking tea beneath the night sky ultimately traces back to microscopic fluctuations in an unimaginably tiny early universe. The cosmos, it seems, has always been surprisingly good at turning tiny differences into enormous consequences. At first, though, the universe was far too hot for anything structured to exist. Atoms couldn't form properly because energetic radiation constantly smashed particles apart. Matter existed more like a dense glowing plasma than anything resembling stars or planets. If you could somehow visit that era, you wouldn't see darkness. You would see brightness everywhere. Blinding, uniform radiation filling all of space. The early universe was less like a starry sky, and more like the inside of a colossal furnace. But expansion changes things. As space stretched outward, temperatures gradually dropped. Around 380,000 years after the Big Bang, the universe finally cooled enough for electrons and protons to combine into stable hydrogen atoms. This moment is called recombination, which sounds pleasantly organised considering it fundamentally changed the visibility of the universe forever. Before recombination, light scattered constantly through the dense plasma. Space was opaque, almost fog-like. Afterward, light could finally travel freely. The glow released during that moment still surrounds us today as the cosmic microwave background radiation, a faint afterglow from the infant universe itself. It's one of the oldest light signals humans can observe, essentially a baby picture of the cosmos. Admittedly a somewhat grainy baby picture taken 13.8 billion years ago with equipment no infant photographer would ever approve of. And after recombination came something surprisingly important. Darkness. Real darkness. Astronomers sometimes call this period the Cosmic Dark Ages, which sounds dramatic enough to involve medieval castles floating through space, but actually refers to a simpler reality. There were no stars yet. The universe had hydrogen gas, it had helium, it had dark matter quietly shaping invisible gravitational scaffolding. But it did not yet possess luminous structures large enough to light the cosmos. Imagine a universe where no star had ever shined. No sunrise had ever happened. No galaxy had yet painted light across space. For millions of years, the cosmos remained mostly dark and cooling. Gravity, however, was already hard at work. Tiny fluctuations left behind by inflation created regions slightly denser than others, and gravity loves density. It gathers matter together relentlessly, patiently, continuously. Regions with a little more mass attracted additional gas. Those regions became denser still, pulling in even more material. Slowly, the first structures began assembling. Dark matter played a major role here, even though scientists still do not know exactly what dark matter is. They know it exerts gravity, and in the early universe, dark matter formed enormous invisible halos that helped ordinary matter collect together. In a sense, dark matter built the framework upon which galaxies would later grow, which is slightly unfair considering dark matter remains invisible, mysterious, and refuses to explain itself despite making up most of the universe's mass. Eventually, hydrogen gas began collapsing into the first stars. These stars were unlike most stars alive today. Modern stars form in environments enriched by heavy elements forged through previous generations of stellar explosions. Carbon, oxygen, iron, silicon, all the ingredients that eventually become planets, oceans, mountains, and very disappointing printer malfunctions. But the first stars had none of that. The early universe contained almost only hydrogen and helium. Astronomers call these primordial stars population 3 stars, which sounds more like a budget apartment complex than ancient stellar titans, but there we are. And these stars may have been enormous. Without heavier elements to cool collapsing gas clouds efficiently, the first stars likely accumulated huge amounts of mass. Some may have reached hundreds of times the mass of our Sun. Massive stars burn hotter, brighter, shorter. They live fast and die violently. A giant primordial star might survive only a few million years before collapsing catastrophically. And this is where things start becoming important for our impossible black hole. Because those first giant stars may have created the earliest black hole seeds. Still, even enormous seeds face a serious challenge. Time. Remember, J0313-1806 appeared only around 670 million years after the Big Bang. That sounds substantial from a human perspective, but cosmically it is astonishingly early. To put it another way, if the entire history of the universe were compressed into a single calendar year, J0313-1806 would already exist within the first couple of weeks after January 1st. Everything afterward, galaxies, planets, dinosaurs, civilization, sandwiches, telescopes, all comes much later. So the question becomes unavoidable. How did something grow so large so quickly in a universe that was still barely assembling its first galaxies? Because galaxies themselves were immature back then. The early cosmos looked very different from the modern universe. Today, galaxies often appear as large organized structures, spirals like the Milky Way, giant ellipticals, stable systems shaped over billions of years. The young universe was messier. Smaller proto-galaxies collided frequently. Gas clouds crashed together. Star formation erupted violently. Radiation flooded regions of space. Everything was denser, hotter, and more chaotic. It was a crowded young cosmos still trying to organize itself. And through all that turmoil, black holes somehow began appearing extraordinarily early. In fact, one of the strangest aspects of quasars like J0313-1806 is their brightness. Black holes themselves emit no light. Once something crosses the event horizon, it vanishes from observable view. But the material falling toward black holes becomes incredibly hot before crossing that boundary. Gas spiraling inward forms an accretion disk, heating to millions of degrees through friction and gravitational compression. The result can outshine entire galaxies. A quasar is essentially a black hole feeding so aggressively that its surroundings blaze with enormous radiation, which means when astronomers observe ancient quasars, they are witnessing black holes in the middle of cosmic overeating competitions. J0313-1806 was not quietly sitting in darkness. It was actively consuming matter at extraordinary rates. That creates another problem. The more aggressively a black hole feeds, the more radiation it emits outward. Eventually that radiation pushes incoming gas away. It becomes harder for the black hole to continue growing rapidly. This feedback process is one reason astronomers struggle to explain how such enormous black holes formed so early. Even under ideal conditions, growth should take time, yet the ancient universe apparently found shortcuts, or loopholes, or perhaps entirely different rules. One possibility is that early black holes formed from unusually massive stellar collapses, instead of beginning at only a few solar masses. Perhaps some primordial black holes started hundreds or thousands of times larger. That would help. But even then, growing to 1.6 billion solar masses remains difficult within such a short cosmic window. Another possibility is even stranger. Maybe some black holes skipped stars entirely. This idea, called direct collapse, proposes that giant clouds of primordial gas collapsed almost straight into black holes without first forming stable stars. Imagine bypassing childhood entirely and appearing immediately as a fully grown cosmic monster. If enormous gas clouds collapsed rapidly enough under the right conditions, they could create black hole seeds vastly larger than ordinary stellar remnants. Instead of starting small and growing patiently, these black holes would begin life already gigantic. Scientists find this idea increasingly attractive because ordinary growth models struggle so badly with objects like J0313-1806. Still, direct collapse requires very specific conditions. The gas cloud must avoid fragmenting into stars. It must remain hot enough. Radiation fields must behave correctly. Angular momentum must be reduced. The whole process becomes rather delicate cosmically speaking, like trying to stack pancakes during an earthquake. And yet perhaps the early universe provided those rare conditions more often than expected. After all, the first galaxies were unlike anything around today. Gas densities were higher, collisions were more frequent, radiation backgrounds differed enormously. The cosmos itself was younger, denser, and evolving rapidly. Maybe that environment allowed black holes to grow with astonishing efficiency. Perhaps the infant universe was simply much better at building monsters than we anticipated. There's another deeply strange aspect to all this as well. The earliest black holes may have helped shape the first galaxies themselves. For years, astronomers debated whether galaxies create black holes or black holes influence galaxy formation. Now, evidence suggests the relationship may be deeply intertwined from the very beginning. When black holes feed aggressively, they release tremendous energy into surrounding space. Radiation and particle jets blast outward, heating nearby gas and influencing star formation. Sometimes this suppresses stellar growth. Other times it may trigger new waves of starbirth. Either way, black holes are not passive objects quietly sitting at galactic centers. They actively reshape their environments. That means ancient quasars like J0313-1806 may have influenced entire regions of the young universe. Imagine that for a moment. When the cosmos itself was still young and mostly dark, these giant feeding black holes already blazed across space like cosmic lighthouses. Some may have outshined every star in their host galaxies combined, and their existence tells us something profound about the pace of cosmic evolution. The universe did not spend billions of years calmly organizing itself before producing extreme objects. Extremes appeared almost immediately, violence came early, complexity emerged quickly. The cosmos wasted very little time experimenting with gigantic structures. This realization has changed how astronomers think about the first billion years after the Big Bang. For a long time, researchers imagined gradual orderly progression. Small structures first, larger systems later, steady hierarchical growth. But discoveries like J0313-1806 suggest the early universe may have been astonishingly efficient at producing massive objects very rapidly, almost alarmingly rapidly. And this raises a fascinating possibility. Perhaps we underestimate how quickly complexity can emerge under the right conditions. Not just in galaxies, but everywhere. Given enough gravity, enough matter, enough time, even if only hundreds of millions of years, the universe begins assembling structures of remarkable sophistication. Stars, galaxies, black holes, chemical elements, eventually biology, eventually consciousness, eventually a species capable of building telescopes to look backward through time and wonder how any of this happened at all. There is something oddly humbling about that chain of events, especially because the light from J0313-1806 began travelling toward Earth, long before our planet existed. At the time that black hole blazed in the darkness, the Milky Way itself was still forming. Our solar system was billions of years away. Earth did not yet exist as even scattered dust, and yet across incomprehensible distances, photons began their journey anyway, travelling through expanding space for over 13 billion years until eventually human beings developed enough technology, mathematics, and curiosity to notice them. Ancient light meeting late arriving intelligence. That may be one of the quiet miracles of astronomy. Every observation becomes a conversation across time, and in the case of J0313-1806, the message arriving from the ancient universe appears to say something rather unsettling. The first cosmic night may not have remained quiet for very long, because while galaxies were only beginning to form, while darkness still dominated huge regions of space, something enormous was already feeding in the shadows. Something impossibly early. Something growing far faster than our models expected. Black holes have a reputation problem. Mention them in conversation, and people immediately picture cosmic vacuum cleaners roaming the universe like hungry monsters, swallowing planets, stars, spaceships, and possibly anyone who forgot to answer an email on time. Science fiction has not exactly helped their image. In reality, though, most black holes are surprisingly ordinary in origin. Not ordinary in the sense that you would want one parked near your neighbourhood, of course, but ordinary in the sense that astronomers understand the basic process reasonably well, at least most of the time, and that most of the time matters enormously, because J0313-1806 appears to belong to the category of black holes that refuse to behave normally at all. To understand why, we first need to walk through the standard story of black hole birth, the version astronomers expected the universe to follow before ancient monsters started appearing far too early and making everyone uncomfortable. The story begins with stars, which when you think about it is already slightly unfair. Stars spend millions or billions of years holding themselves together through a delicate balancing act, only to occasionally end their existence by collapsing so violently they tear holes into space-time itself. Rather dramatic behaviour for giant floating balls of gas. Still, stars are essentially battles between two competing forces. Gravity pulls inward, fusion pushes outward. Inside a star's core, enormous pressure squeezes hydrogen atoms together until they fuse into helium. That fusion releases energy, and the outward pressure from that energy resists gravitational collapse. As long as fusion continues, the star survives. The balance holds. Our own sun is currently in this stable phase. It has been calmly converting hydrogen into helium for roughly 4.6 billion years, and should continue doing so for several billion more. Quite reassuring, really. No immediate cosmic catastrophes scheduled, but stars do not possess infinite fuel supplies. Eventually, hydrogen in the core begins running low. The balance changes. Gravity starts gaining the upper hand. What happens next depends mostly on mass. Smaller stars, including our Sun, live relatively peaceful lives by stellar standards. When they exhaust core hydrogen, they expand into red giants, shed outer layers, and eventually leave behind dense remnants called white dwarfs. No black hole, no space-time rupture, just a hot, compact stellar ember gradually cooling over immense periods of time. Massive stars are another matter entirely. A star significantly heavier than the Sun burns fuel far more rapidly. Higher mass means stronger gravity, which creates hotter cores, which accelerates fusion dramatically. It's rather like driving a car permanently at maximum speed while wondering why the fuel tank empties so quickly. Some massive stars live only a few million years before reaching the end, and their endings are violent. Once fusion can no longer support the core against gravity, collapse begins almost instantly. The core implodes inward at enormous speed, temperatures soar, pressure becomes extreme beyond ordinary imagination. Then comes the explosion, a supernova. For a brief time, a dying star can outshine an entire galaxy. Heavy, elements forged within the star blast outward into space. Carbon, oxygen, iron, calcium, the ingredients that eventually become planets, oceans, mountains, bones, teeth, and regrettably fragile coffee mugs. Every atom of iron in your blood was once cooked inside a star that died violently long before the sun existed. Human beings, in a very literal sense, are assembled from stellar debris, which sounds poetic until you realise it also means parts of your body were launched across the galaxy by ancient exploding suns. The universe has surprisingly chaotic manufacturing methods. After the supernova, what remains depends again on mass. Some stellar cores compress into neutron stars, objects so dense that a teaspoonful would weigh billions of tons. Others continue collapsing, and if enough mass is concentrated into a sufficiently small region, gravity becomes unstoppable. No known force can halt the collapse. The result is a black hole. Now, black holes are often described as objects with gravity so strong that not even light can escape, which is true, but also slightly incomplete. The truly strange thing about black holes is not merely their strength, it's the geometry they create. According to Einstein's general relativity, gravity is the curvature of space-time itself. Massive objects bend the fabric around them. Earth bends space a little. The sun bends it more. Black holes bend it catastrophically. At the centre lies the singularity, a region where matter is compressed beyond known physical description. Density appears to become effectively infinite. Our equations stop behaving sensibly there. Physicists generally interpret this as a sign that our understanding is incomplete, rather than nature literally producing infinities, but either way it means current theories break down. Around the singularity lies the event horizon. This is the famous boundary beyond which escape becomes impossible. Importantly, the event horizon is not a physical surface. A spaceship crossing it would not slam into a wall or bounce dramatically backward while orchestral music intensified. In fact, if the black hole were large enough, crossing the event horizon might initially feel surprisingly uneventful, which somehow makes it more unsettling. The real danger appears afterward. Once inside the horizon, all paths through space-time lead inward. Escape becomes as impossible as travelling backward into yesterday. Gravity eventually stretches objects tremendously through tidal forces in a process delightfully nicknamed spaghettification. Astronomers do occasionally choose wonderfully silly terminology for deeply horrifying events. Still, despite their strange properties, stellar black holes follow understandable rules. A massive star lives. It dies. The core collapses. A black hole forms. Straightforward enough. And for decades, astronomers assumed supermassive black holes probably grew from these stellar beginnings. Start with a relatively small black hole, perhaps 10 or 20 solar masses. Feed it gas. Allow mergers with other black holes. Wait patiently for millions or billions of years. Eventually you can produce giants. This gradual growth model works reasonably well for many black holes in the modern universe. Sagittarius A star, the black hole at the centre of the Milky Way, likely grew through long-term accumulation over billions of years. Even then, it only reached around 4 million solar masses. J0313-1806, meanwhile, reached roughly 1.6 billion solar masses in less than 700 million years after the Big Bang. That difference is the cosmic equivalent of planting a seed on Monday and discovering Mount Everest in your backyard by Thursday afternoon. Something about the ordinary process suddenly seems inadequate. because black holes cannot grow infinitely fast. This is one of the most important parts of the puzzle. People often imagine black holes swallowing matter instantly like cosmic drainpipes, but reality is much slower and messier. Matter falling toward a black hole usually forms a rotating disk first. Angular momentum prevents gas from plunging directly inward immediately. The material spirals gradually toward the center. Friction within the disk heats the gas tremendously. As the gas becomes hotter, it emits radiation outward, and that radiation pushes back against incoming material. Astronomers describe this balancing point through something called the Eddington limit. The idea is fairly intuitive. Imagine trying to eat soup while a powerful fan blows directly into your face. At some point, consuming additional soup becomes difficult no matter how enthusiastic you remain. Black holes encounter a similar problem. Feed too aggressively, and outgoing radiation begins pushing material away faster than gravity can pull it inward. This naturally limits growth rates. Under ordinary Eddington limited feeding, a stellar black hole requires enormous spans of time to become supermassive. Too much time, in fact, for J0313-1806. That's why astronomers became uneasy. Even if an early star collapsed into a reasonably large seed black hole, perhaps 100 solar masses or more, standard growth rates still struggle to explain how it reached billions of solar masses so quickly. There simply was not enough cosmic time available. Researchers started running simulations. Again and again, the same problem appeared. Too slow. Always too slow. Unless black holes in the early universe fed far above the Eddington limit for extended periods, or began life vastly larger than expected, or formed through some entirely different mechanism altogether. And this is where the story starts becoming truly strange. Because the first stars themselves may not have resembled modern stars very much. The early universe lacked heavy elements. That matters more than it might initially seem. Elements heavier than helium help gas cool efficiently. Cooling allows clouds to fragment into many smaller stars. Without heavy elements, primordial gas clouds may have formed fewer but much larger stars. Some population 3 stars may have exceeded several hundred solar masses, perhaps even more. These gigantic stars would have lived extremely short, violent lives, and their collapses could produce unusually massive black hole seeds. This helps somewhat. A larger seed requires less subsequent growth, but even enormous stellar seeds struggle to solve the full problem. Suppose you begin with a black hole containing several hundred solar masses. Growing it into 1.6 billion solar masses within 670 million years still demands extremely aggressive feeding almost continuously. And continuous feeding is difficult because black holes are messy eaters. Radiation disrupts incoming gas. Nearby star formation changes environments. Explosions disturb surrounding matter. Galactic collisions alter gas flows. Maintaining uninterrupted rapid growth becomes remarkably challenging. It's a little like trying to keep a candle lit during a hurricane, while simultaneously cooking dinner and rebuilding the kitchen. Possible perhaps under ideal conditions, but not easy. There is another issue as well. Young galaxies were small. Remember, the universe itself was still in its infancy when J0313-1806 existed. Galaxies had not yet fully matured. Many proto-galaxies contained far less mass than modern giants. So where did enough fuel come from? A black hole reaching billions of solar masses requires staggering amounts of matter. The host environment must continuously supply enormous gas reservoirs inward. That means the galaxy surrounding J0313-1806 was itself evolving extraordinarily rapidly. Astronomers suspect the young universe may have been unusually efficient at funneling gas toward galactic centers. Frequent mergers and dense environments could help channel material inward. Still, the pace remains astonishing. At this point, scientists began entertaining alternatives. What if the standard stellar route was not the primary path for early supermassive black holes? What if some black holes skipped the normal process entirely? This idea leads toward direct collapse models, which we'll explore more deeply later, but the basic concept is wonderfully dramatic. Instead of beginning as stars, enormous gas clouds collapse almost directly into giant black holes. No prolonged stellar stage, no small beginnings, just immediate formation of massive seeds. If true, this changes the narrative completely. The first black holes may not have been tiny remnants patiently growing over billions of years. Some may have started life already immense, and that possibility reshapes how astronomers think about the young universe itself, because it suggests the cosmos was capable of building extreme objects extraordinarily early under the right conditions. There's another fascinating detail hidden inside this problem. Black holes are not rare accidents. They appear deeply connected to galaxy evolution everywhere astronomers look. Nearly every large galaxy examined carefully seems to contain a supermassive black hole at its centre. Moreover, black hole mass often correlates with properties of the surrounding galaxy. Larger galaxies tend to host larger central black holes. This relationship suggests galaxies and black holes evolve together somehow, like dance partners influencing each other continuously across cosmic history, which raises an intriguing possibility about the early universe. Perhaps black holes were not secondary features appearing after galaxies matured. Perhaps they were central participants from the beginning. Perhaps giant black holes helped organize the earliest galaxies around themselves. In that sense, J0313-1806 may not merely represent an impossible object. It may represent a clue about how cosmic structure formed altogether. And the more astronomers studied ancient quasars, the more they realized these objects were not isolated oddities. The early universe contained multiple supermassive black holes appearing uncomfortably early. Each discovery pushed theoretical models harder. Each new observation suggested rapid black hole growth was not impossible in practice, because apparently the universe kept doing it. At some point, reality becomes difficult to argue with. There is something wonderfully humbling about that process in science. Researchers construct elegant theories. Equations behave beautifully. Simulations evolve logically. Then the universe quietly reveals something enormous and ancient that should not exist yet. And suddenly everyone returns to the drawing board carrying coffee and existential concern. J0313-1806 belongs firmly to that category. It forces astronomers to reconsider how black holes are born, how galaxies evolve, and how quickly complexity emerged after the Big Bang. Maybe the first stars were larger, maybe feeding rates exceeded expectations, maybe direct collapse occurred, maybe several mechanisms worked together simultaneously, or maybe some entirely new physics remains hidden in the darkness of the early universe, waiting to be discovered. For now, the ordinary story of stellar collapse remains essential because it provides the baseline. It tells us how black holes usually form, and once you understand the usual process, the impossible nature of J0313-1806 becomes much clearer. This black hole did not merely grow large, it grew large too quickly. So quickly that ordinary stellar birth followed by conventional feeding appears barely capable of explaining it, which means we are left staring toward the ancient cosmos, wondering whether the first generation of stars behaved in ways far more extreme than modern astronomy originally imagined. There is something slightly absurd about the way astronomers study black holes. After all, black holes are famously invisible. They do not shine. They do not reflect light. They do not politely sit beneath giant cosmic spotlights, waiting to be photographed from flattering angles. And yet scientists regularly estimate their masses, track their behaviour, map their surroundings, and occasionally discover that one of them grew into a billion solar mass monster before the universe was even old enough to properly grow galaxies, which naturally raises an important question. How exactly do you weigh something you cannot see? The answer, rather fittingly, is that astronomers study everything around the black hole instead. Because black holes may hide themselves, but they are terrible at hiding their effects, especially when they are feeding, and J0313-1806 was feeding with extraordinary enthusiasm. To understand how astronomers discovered this object in the first place, we need to imagine the challenge facing modern telescopes. When researchers observe distant parts of the universe, they are also looking backward through time. Light takes time to travel. The farther away an object is, the older the light we receive from it. Sunlight reaching Earth takes about 8 minutes. Light from Neptune requires several hours. Light from the Andromeda Galaxy travels roughly 2.5 million years before arriving here. J0313-1806 lies vastly farther away than that. The photons reaching Earth from this object began their journey more than 13 billion years ago. Those ancient photons travelled across expanding space, while galaxies evolved, stars exploded, continents formed, dinosaurs appeared and vanished, mammals diversified, and eventually one rather curious primate species invented telescopes. By the time the light finally arrived, the black hole itself had already existed in the distant past for billions upon billions of years. Astronomy, in many ways, is the study of delayed information. Everything we see already happened, and the deeper we look into space, the earlier the universe becomes. Now, spotting extremely distant objects is difficult enough on its own. Ancient galaxies are faint. Early stars are tiny against the enormous cosmic backdrop. Expansion stretches light toward longer wavelengths as it travels. This stretching effect is called redshift. As space expands, light waves themselves become stretched. Visible light emitted billions of years ago may arrive today shifted into infrared wavelengths. The greater the redshift, the farther away and earlier in cosmic history the object exists. Astronomers use redshift almost like a cosmic timestamp, and J0313-1806 carried an astonishing one. Its measured redshift placed it at a time when the universe was only around 670 million years old. That immediately attracted attention. But distance alone was not the only surprise. The object was unbelievably bright. Remember, black holes themselves emit no light. The brightness comes from matter surrounding them as it spirals inward through the accretion disk. Gas falling toward a supermassive black hole becomes compressed and heated to extraordinary temperatures. Friction inside the disk produces enormous radiation across multiple wavelengths. The result is a quasar. Quasars are among the brightest objects in the universe. Some outshine entire galaxies containing hundreds of billions of stars, which is almost comically excessive when you think about it. Imagine replacing every light bulb in a major city with one aggressively overachieving gravitational catastrophe. That still might undersell a quasar. J0313-1806 belonged to this category. Its quasar blazed across the early universe so intensely that astronomers could detect it despite the unimaginable distance involved. And brightness itself contains clues. A quasar's luminosity helps scientists estimate how much matter the black hole is consuming. The hotter and brighter the accretion disk, the more actively material is falling inward. But brightness alone does not directly reveal mass. For that, astronomers rely on motion. Specifically, they study the gas orbiting near the black hole. This is one of the elegant tricks of astrophysics. Gravity governs movement. By observing how quickly matter travels around an unseen object, scientists can infer how massive that object must be. It's the same principle that lets us estimate the mass of Earth by studying the Moon's orbit, or the Sun's mass by examining planetary motion. Invisible things reveal themselves through gravity. Near a supermassive black hole, gas clouds orbit at tremendous speeds. The stronger the gravity, the faster the gas must move to remain in orbit. Astronomers examine specific spectral lines emitted by this gas. As the gas moves, those spectral lines broaden due to the Doppler effect. Material moving toward us shifts slightly one way. Material moving away shifts another. The faster the motion, the broader the observed lines become. By measuring that broadening carefully, researchers estimate orbital speeds. Then comes the mathematics, and the mathematics pointed towards something enormous, roughly 1.6 billion solar masses. At first glance, that number becomes almost meaningless because human brains are not naturally designed to visualize billion solar mass gravitational monsters. So let's slow down for a moment. Our Sun contains about 99.8% of all the mass in the solar system. Every planet, moon, asteroid, comet, grain of dust and regrettably lost sock in orbit around the Sun together make up only a tiny fraction compared to the Sun itself. Now multiply the Sun's mass by 1.6 billion. That is approximately the estimated mass of J0313-1806. And all of that mass compressed into a region smaller than the orbit of our solar system. The scale becomes difficult to absorb. If such a black hole replaced the Sun, the event horizon itself would extend far beyond the planets. Mercury gone, Venus gone, Earth gone, Mars gone. Possibly a very concerned Jupiter wondering what exactly happened to the neighbourhood. And yet despite its immense mass, the black hole itself would remain completely dark. Only the surrounding disk of infalling material would blaze brilliantly. That distinction matters because quasars represent feeding events, not merely black holes sitting quietly. J0313-1806 was not dormant. It was actively growing, violently. Astronomers estimated the black hole was consuming matter at astonishing rates close to the theoretical Eddington limit. That means radiation pressure and gravitational attraction were approaching equilibrium. The black hole was essentially feeding as rapidly as physics comfortably allows under ordinary conditions, which immediately intensified the mystery. Because if J0313-1806 was already 1.6 billion solar masses while feeding near maximum rates, then its growth history must have been extraordinarily aggressive from very early times. There simply was not room for laziness anywhere in the timeline. Every stage had to proceed quickly, stars forming quickly, seeds collapsing quickly, gas accreting quickly, galaxies assembling quickly. The entire process resembles a cosmic construction project completed suspiciously ahead of schedule. Naturally, astronomers began examining the surrounding environment, and that environment proved fascinating as well. Observations suggested J0313-1806 lived inside a galaxy, experiencing intense star formation. Huge amounts of gas flowed through the system. Stellar birth rates may have reached hundreds of solar masses per year. For comparison, the Milky Way forms only about 1 or 2 solar masses worth of stars annually today. So this ancient galaxy was essentially operating like a cosmic factory running every machine simultaneously, while sparks flew across the ceiling. The black hole itself may also have been driving enormous outflows. Quasars often produce powerful winds generated by radiation and energetic processes near the accretion disk. In J0313-1806, these outflows appeared exceptionally fast, perhaps reaching around 20% of the speed of light. That is not merely windy. That is material leaving the system at roughly 60,000 kilometers per second, fast enough to circle Earth more than once every second. These outflows matter because they influence galaxy evolution. Powerful quasar winds can heat surrounding gas or even blast it outward entirely, suppressing future star formation. So while the black hole fed aggressively, it may simultaneously have been disrupting the very galaxy providing its fuel. Rather self-destructive behaviour in a way, a little like eating your kitchen while preparing dinner. This relationship between black holes and galaxies has become one of the central themes of modern astronomy. For decades, black holes were often treated almost as secondary objects sitting quietly at galactic centres. Now, astronomers increasingly suspect they play major roles in shaping galaxies themselves. Supermassive black holes regulate star formation. They influence gas dynamics. They generate energetic feedback. They may even affect the long-term evolution of galactic structure. And in the young universe, those effects could have been even more dramatic. Because conditions were denser, collisions more frequent, gas more abundant. Everything happened faster. J0313-1806 offers a glimpse into that violent youth. It shows us a universe still assembling itself while simultaneously producing some of the largest black holes ever observed. There is something wonderfully unsettling about that combination. We tend to imagine cosmic history unfolding gradually and neatly. Small things first, larger structures later, order emerging step by step. But the early universe appears to have been startlingly ambitious. Only a few 100 million years after the Big Bang, gigantic black holes already blazed across space. That changes how astronomers think about cosmic timelines altogether. It also creates philosophical discomfort in a very scientific sort of way, because black holes represent regions where our understanding becomes incomplete. General relativity predicts them successfully. Quantum mechanics struggles with them profoundly. Information behaves strangely near them. Time distorts around them. Singularities signal breakdowns in known theory. And now, J0313-1806 adds another layer of confusion by existing too early. It is almost as though black holes continually search for new methods of annoying physicists. First they bend space-time, then they challenge quantum theory, then they appear billions of solar masses too soon. One begins to suspect malicious intent. Of course, astronomers respond to such mysteries not with despair, but with more telescopes. Humanity's standard scientific reaction to confusion is apparently, we should build a larger mirror. And indeed, new observatories are transforming our understanding of the early universe rapidly. Infrared instruments became especially important because ancient light arrives stretched into longer wavelengths. Ground-based observatories in Chile, Hawaii, and elsewhere contributed enormously to identifying distant quasars. Then came space telescopes capable of seeing even deeper. The James Webb Space Telescope in particular has opened remarkable new windows into the infant cosmos. Designed specifically to observe infrared light with extraordinary sensitivity, it allows astronomers to study some of the earliest galaxies and black holes ever detected. And what Webb is finding often appears surprisingly mature. Galaxies larger than expected, structures appearing earlier than anticipated, black hole candidates forming rapidly. The young universe increasingly looks less like a calm, gradual beginning and more like an aggressively productive cosmic startup company operating on impossible deadlines. Some researchers now wonder whether our assumptions about early structure formation require significant revision. Perhaps primordial gas behaved differently than expected. Perhaps black hole seeds formed larger. Perhaps feeding rates exceeded traditional limits under certain conditions. Or perhaps dark matter played a more active role in rapid collapse scenarios. There are even more speculative ideas. Some theorists explore whether primordial black holes formed directly from density fluctuations shortly after the Big Bang itself. Others investigate modifications to conventional cosmological models. Most of these ideas remain uncertain, but uncertainty is exactly what objects like J0313-1806 generate. And that uncertainty is valuable. Science advances most rapidly when observations stop fitting comfortably inside established frameworks. A perfectly predictable universe would be deeply boring scientifically. Interesting discoveries occur when reality refuses cooperation. J0313-1806 represents one of those moments. An ancient object forcing modern astronomy to reconsider how quickly complexity emerged after the Big Bang. A monster from the early universe announcing itself through ancient photons after travelling more than 13 billion years across expanding space. And all because astronomers learned how to weigh invisible things by watching gravity move the universe around them. Which is rather beautiful when you think about it. No one has ever directly seen a black hole itself. What we see are consequences: motion, heat, radiation, distortion. Gravity revealing the presence of hidden giants, and in the case of J0313-1806, those consequences revealed something astonishing. A black hole already enormous while the cosmos itself was still young, a gravitational monster blazing in darkness before galaxies had properly matured. One of the strangest things about the universe is that it keeps track of time whether we are paying attention or not. Stars age, galaxies evolve, atoms decay, space expands. Everything moves forward according to cosmic clocks that began ticking long before Earth existed, and will continue long after our species is gone. And most of the time those clocks behave quite reliably. Astronomers have become remarkably good at reconstructing cosmic history. By studying expansion rates, radiation, stellar, evolution, and galactic motion, scientists can estimate the ages of stars, galaxies, and distant structures with extraordinary precision. In many ways, modern cosmology resembles forensic investigation on the largest possible scale. Researchers arrive billions of years after the fact, examine the evidence carefully, and attempt to reconstruct what happened. The universe leaves clues everywhere: ancient light, chemical fingerprints, gravitational effects, the distribution of galaxies, the cooling of radiation. Even black holes contribute evidence, although they do so with the slightly annoying habit of hiding the most important parts behind event horizons. Still, despite all this complexity, the overall timeline of cosmic history is fairly well understood. The universe began around 13.8 billion years ago. The first atoms formed several 100,000 years later. The first stars emerged after tens or hundreds of millions of years. Galaxies gradually assembled. Larger structures grew over time. Everything followed a sequence, and sequence matters enormously, because time is not infinitely available. That may sound obvious, but it lies at the heart of the problem surrounding J0313-1806. The issue is not merely that the black hole became large, it became large too early. There was not enough time, and in cosmology, insufficient time is a serious problem. You can think of the universe as operating under enormous but still finite schedules. Processes require duration. Structures need time to form. Gravity works steadily but not instantly. A galaxy cannot simply appear fully assembled moments after the Big Bang like a cosmic pop-up tent. Likewise, black holes require growth, at least under ordinary circumstances. To understand the cosmic clock problem properly, it helps to imagine compressing the history of the universe into a much shorter timescale. Suppose the entire 13.8 billion year history of the cosmos were condensed into a single 24-hour day. The Big Bang happens at midnight. The Milky Way begins forming several hours later. The sun appears only during the evening. Human civilization arrives in the final seconds before midnight. Under this compressed timeline, J0313-1806 already exists astonishingly early in the morning, before most large cosmic structures should reasonably have had time to mature. That is what troubles astronomers. The black hole appears rushed, as though the universe somehow skipped intermediate steps, and the mathematics behind black hole growth only deepen the discomfort. Let's return for a moment to the ordinary picture. A massive star collapses, a black hole forms. Perhaps it begins at around 10 solar masses, maybe larger if the original star was enormous. Then the feeding process starts. Gas falls inward, mass increases. Over millions or billions of years, the black hole gradually grows. Straightforward enough, but growth under realistic conditions has limits. One of the key constraints comes from the Eddington limit, which we touched on earlier. This is essentially the maximum stable feeding rate before outgoing radiation begins pushing in falling material away. If a black hole feeds too aggressively, it creates enough radiation pressure to disrupt the very gas trying to fall inward. Nature imposes a speed limit. Astronomers can calculate how quickly a black hole should grow under Eddington limited accretion, and here the numbers become problematic. Very problematic. Even starting with a reasonably large seed black hole, perhaps 100 solar masses, continuous Eddington limited feeding still struggles to produce a billion solar mass giant within only 670 million years. especially because the process would need to proceed almost uninterrupted. No major starvation periods, no long interruptions, no significant disruptions from explosions, galactic turbulence, or competing star formation. The black hole would need to feed almost continuously from extremely early cosmic times, which is difficult because the early universe was chaotic. Galaxies collided frequently, radiation flooded environments, gas dynamics changed rapidly, stars exploded, everything was unstable. Maintaining perfect long-term feeding under those conditions becomes challenging. Astronomers began running simulations. Repeatedly, the same conclusion emerged again and again. Ordinary growth models barely work, and in many cases they fail completely. This is why J0313-1806 represents not merely a discovery but a timing crisis. The cosmic clock appears too short. Imagine planting a sapling and returning a week later to discover a fully grown redwood forest, complete with hiking trails and mildly overpriced gift shops. At some point, you stop asking whether the tree grew quickly and start wondering whether your understanding of trees is fundamentally incomplete. The same thing happened here. Researchers realized that if the timeline itself creates impossible constraints, then at least one assumption must change. Either black holes formed much earlier than expected, or they grew much faster than expected, or they began vastly larger than expected, possibly all three. This tension has become one of the major puzzles in modern cosmology, and intriguingly, J0313-1806 is not alone. Other ancient quasars have also appeared unexpectedly early. Several supermassive black holes from the first billion years of cosmic history now challenge conventional models. Each discovery sharpens the problem, because one strange object might represent an anomaly. Multiple objects suggest a pattern. At that point, astronomers must confront an uncomfortable possibility. Maybe the early universe itself behaved differently than we imagined. One proposed solution involves super-Eddington accretion. This idea suggests black holes in the young universe, occasionally fed faster than the traditional Eddington limit allows. Under certain conditions, geometry and gas flows may trap radiation efficiently enough that matter continues falling inward despite enormous luminosity. Essentially, the black hole manages to eat faster without blowing all the food away. Scientists are actively exploring this possibility because even temporary periods of super-Eddington growth could dramatically accelerate black hole evolution. Still, sustaining such feeding over long periods remains difficult. Black holes are messy systems. Accretion disks become unstable. Radiation creates turbulence. Magnetic fields complicate flows. The entire process resembles trying to pour soup into a spinning fan during a thunderstorm, while gravity itself bends space nearby. Astrophysics is wonderfully unreasonable sometimes. Another proposed solution focuses on the seeds themselves. Perhaps early black holes did not begin at only tens or hundreds of solar masses. Perhaps they started enormously larger. This is where direct collapse models become attractive. Instead of forming from ordinary stellar remnants, giant primordial gas clouds may have collapsed almost directly into black holes containing tens of thousands or even hundreds of thousands of solar masses. That changes the timeline dramatically. A black hole starting at 100,000 solar masses requires far less subsequent growth to reach billions. The cosmic clock becomes less restrictive, but direct collapse introduces new challenges. The collapsing gas cloud must avoid fragmenting into stars first. Cooling processes must behave carefully. Radiation backgrounds must remain within specific ranges. The conditions become delicate. Possible, perhaps, but not guaranteed. And yet the universe only needs such conditions occasionally to produce giant early quasars. There is another fascinating aspect to this timing problem as well. The first billion years after the Big Bang may have unfolded much more rapidly than humans instinctively imagine. Cosmic history sounds enormous because billions of years exceed ordinary comprehension. But the early universe was denser than today. Matter existed closer together. Interactions occurred more frequently. Everything happened faster. Galaxies merged rapidly. Gas collapsed efficiently. Star formation rates soared. The infant cosmos was not calm. It was crowded, energetic, and evolving continuously. In some ways, the young universe resembled a cosmic construction site operating at maximum capacity. Still, even under those intense conditions, J0313-1806 remains difficult to explain fully, because its mass pushes near the edge of what many models can comfortably accommodate, and the farther astronomers push observations toward earlier times, the more strange objects appear. The James Webb Space Telescope has intensified these discussions significantly. Webb's infrared capabilities allow astronomers to peer deeper into the early universe than ever before, and many of its observations suggest that galaxies and structures formed surprisingly rapidly. Some early galaxies appear larger, brighter, or more mature than expected. Now, it is important not to overstate this. Cosmology itself is not collapsing into chaos. The Big Bang model remains enormously successful overall, but details matter, and the details increasingly suggest the first cosmic structures may have evolved with startling speed. Scientists occasionally refer to this as a tension problem, a wonderfully calm phrase meaning the observations and the theory are currently staring at each other awkwardly. The cosmic clock problem surrounding J0313-1806 sits directly inside that tension. Time appears insufficient, and when time itself becomes the obstacle, astronomers must rethink growth histories altogether. There's also a more philosophical side to this puzzle. Human beings naturally assume complexity requires long durations, and often it does. Life on Earth evolved over billions of years. Civilizations rise gradually, mountains form slowly, forests grow patiently. So when we encounter enormous black holes shortly after the Big Bang, something feels intuitively wrong. It seems too fast. But perhaps the universe is simply more efficient under extreme conditions than we are accustomed to imagining. After all, our gravity is relentless. Given dense enough environments and enough matter, collapse accelerates rapidly. Maybe the early cosmos possessed ideal conditions for building giant structures quickly, or perhaps black holes themselves help accelerate their own growth indirectly by shaping surrounding galaxies and funneling gas inward. There is still much researchers do not know, and honestly that uncertainty is one of the healthiest aspects of science. The cosmic clock problem exists precisely because observations improved. Better telescopes revealed deeper history. Deeper history revealed impossible objects. Impossible objects forced new questions. That is progress. Astronomy advances not by preserving comfort, but by confronting contradiction. J0313-1806 represents one of those contradictions. An object ancient enough to challenge timelines, massive enough to strain conventional growth models, bright enough to be seen across more than 13 billion years of expanding space, and all of it happening while the universe itself was still in cosmic childhood. There is something almost eerie about that image. Imagine standing in a newborn forest where tiny saplings have only just emerged from the soil. Then somewhere in the distance, impossibly, towers a fully grown mountain-sized tree older and larger than everything around it. You would not merely admire the tree, you would question the forest itself. That is essentially what astronomers are doing now. J0313-1806 forces researchers to examine the assumptions underlying early cosmic evolution. How fast can matter collapse? How rapidly can galaxies form? How efficiently can black holes feed? Did entirely different formation pathways exist? Could unknown physics influence early growth? These questions matter far beyond a single quasar, because supermassive black holes appear everywhere in the universe today. If ancient giants formed rapidly, then understanding them may reveal fundamental truths about galaxy evolution itself. The earliest black holes could have shaped the cosmos in profound ways from the very beginning. And perhaps that is the most remarkable part of all. When we look deep enough into space, we do not merely see old objects. We see the universe experimenting, trying structures, testing extremes, building monsters astonishingly early. The cosmic clock says there should not have been enough time, and yet, the ancient light arriving from J0313-1806 insists otherwise, which means the next question becomes unavoidable. If ordinary black hole growth appears too slow, then exactly how could something feed fast enough to become this enormous before the universe itself had properly grown up? Black holes are often described as cosmic eating machines, which is technically true, but it also creates a slightly misleading impression. People tend to imagine black holes swallowing matter instantly and endlessly, like bottomless drains in space-time with absolutely no table manners. Reality is far less efficient. In fact, one of the great frustrations in astrophysics is that black holes are surprisingly difficult to feed quickly, which becomes a serious inconvenience when you're trying to explain how a monster like J0313-1806 reached 1.6 billion solar masses while the universe was still extraordinarily young. Because under normal conditions, black holes are limited by their own success. The more material they consume, the brighter they become. The brighter they become, the harder additional feeding gets. It is one of those wonderfully ironic cosmic situations where overeating eventually interferes with future overeating. To understand why this happens, we need to picture the environment around a feeding black hole properly. Matter falling toward a black hole does not simply plunge straight inward all at once. Gas clouds possess angular momentum, meaning they rotate. As material spirals inward, it forms an accretion disk around the black hole. This disk becomes extremely hot. Friction between orbiting layers generates enormous temperatures. Gas near the inner regions may heat to millions of degrees. Radiation pours outward across the electromagnetic spectrum. That radiation carries energy, and energy pushes. At low feeding rates, gravity wins comfortably. Matter continues spiraling inward. The black hole grows steadily. But as feeding intensifies, outgoing radiation pressure becomes increasingly important. Eventually, the radiation pushing outward balances gravity pulling inward. This balance defines the Eddington limit. Named after astrophysicist Arthur Eddington, who presumably did not realize his name would eventually become associated with giant ancient black holes, causing cosmological anxiety. The Eddington limit is not an absolute wall. Black holes do not suddenly stop eating once they reach it, but it represents a practical threshold where stable feeding becomes much more difficult. Push beyond it too aggressively, and radiation starts blowing incoming gas away. It becomes harder for matter to reach the event horizon. Imagine trying to pour sand into a leaf blower. The stronger the blower becomes, the more difficult it is to add additional sand. A feeding black hole creates something similar, and this naturally slows growth. Astronomers can calculate how quickly a black hole should gain mass under Eddington-limited accretion. The numbers are fairly unforgiving. If you begin with a small stellar mass black hole and allow perfectly steady Eddington feeding, growth still takes enormous amounts of time, too much time usually for J0313-1806. That is why researchers started considering an uncomfortable possibility. What if early black holes occasionally fed faster than physics seems to prefer? This idea is called super-Eddington accretion, and while it sounds like something involving dramatically overclocked computers and smoke pouring from cosmic machinery, it is actually a serious area of astrophysical research. The key insight is that the Eddington limit assumes fairly idealized conditions. Real accretion disks are messy, very messy. Gas flows become turbulent. Magnetic fields twist through the disk. Radiation may escape unevenly. Matter can clump together. Geometry changes continuously. Under certain circumstances, black holes may temporarily consume material faster than traditional models predict. One important concept here involves photon trapping. Normally, radiation generated inside the accretion disk escapes outward efficiently, pushing against incoming matter. But if infalling gas becomes extremely dense, radiation can become trapped inside the flow itself. Instead of escaping immediately, photons are dragged inward along with the gas. That reduces outward pressure, and if outward pressure weakens, more matter can continue falling inward. Essentially, the black hole manages to smother some of its own radiation beneath overwhelming gas inflow, rather like trying to shout while buried beneath an avalanche of soup. Not an especially dignified image perhaps, but astrophysics occasionally demands sacrifices. These Super Eddington phases could dramatically accelerate black hole growth. Even relatively brief episodes might help explain how early black holes became so enormous so quickly. And the early universe may have provided ideal conditions for such feeding. Remember how different the cosmos was back then. Galaxies were smaller but denser. Gas reservoirs were abundant. Collisions happened frequently. Matter had not yet been locked away inside long-lived stable structures. Everything remained highly dynamic. Young galaxies often funneled huge amounts of gas toward their centers. Gravitational interactions during mergers could drive matter inward efficiently, feeding central black holes aggressively. Under those conditions, perhaps some black holes entered prolonged periods of near-chaotic growth, eating continuously, rapidly, violently. Still, there are limits even here. Sustaining super Eddington accretion for extended durations is difficult. Accretion disks become unstable, radiation eventually escapes, outflows develop, jets form, magnetic turbulence complicates everything further. Nature does not hand out billion solar mass black holes easily. And that is exactly why J0313-1806 remains so fascinating. Because whatever happened, it appears to have worked astonishingly well. Some researchers now suspect the early universe may have hosted entire populations of rapidly feeding black holes hidden behind thick cocoons of gas and dust. These systems might have grown quickly while much of their radiation remained obscured. In a sense, giant black holes may have spent part of their youth hidden beneath dense cosmic blankets, while quietly becoming enormous. There is something oddly amusing about imagining one of the universe's largest gravitational monsters essentially hiding under the covers while overeating. But another complication appears here. Feeding black holes do not merely absorb matter, they also influence everything around them. As material spirals inward, some energy escapes through powerful jets and winds. These outflows can become extraordinary. In some quasars, radiation-driven winds travel at significant fractions of light speed. J0313-1806 itself appears to produce remarkably powerful outflows. That creates a paradoxical situation. The black hole requires enormous amounts of gas to grow, but the energy released during feeding can blast surrounding gas outward, disrupting the very supply needed for continued growth. It is rather like trying to fill a bathtub while simultaneously punching holes in the pipes. This feedback process plays a major role in modern galaxy evolution theories. Supermassive black holes regulate star formation inside galaxies through energetic feedback. If too much gas accumulates near the center, the black hole feeds aggressively and releases energy outward. That energy heats or expels gas, slowing future feeding and suppressing additional star formation. The galaxy and black hole effectively regulate each other. Astronomers increasingly believe this relationship helped shape the modern universe. But in the early cosmos, perhaps these feedback cycles behaved differently. Maybe gas inflows were so overwhelming that feedback could not fully stop them. Or perhaps mergers repeatedly delivered fresh reservoirs of fuel faster than outflows could clear them away. The infant universe may have operated under conditions modern galaxies rarely experience. And there is another important detail. Black hole feeding efficiency depends strongly on spin. Yes, black holes spin. Quite rapidly sometimes. As matter falls inward, it transfers angular momentum to the black hole. Over time, the black hole can rotate at tremendous rates. Spin changes the structure of space-time near the event horizon itself. It affects accretion disk behavior. It influences jet formation. And it alters how efficiently gravitational energy converts into radiation. Highly spinning black holes can extract enormous energy from infalling material. That increased efficiency produces more radiation, which sounds helpful until you remember radiation also resists further feeding. So paradoxically, a highly efficient feeding process may actually slow long-term growth under certain conditions because it generates stronger outward pressure. Meanwhile, less efficient accretion allows more mass to cross the horizon while producing comparatively less disruptive radiation. Sometimes being messy is advantageous. The universe has a surprising number of situations where inefficiency turns out to be useful. Researchers now build increasingly sophisticated simulations attempting to model these processes, and the simulations are extraordinarily complicated. Gas dynamics alone become chaotic. Add radiation transport, magnetic fields, relativistic effects, turbulence, star formation, supernova explosions, dark matter halos, and galactic mergers, and the entire system becomes a computational nightmare. Modern supercomputers spend enormous amounts of time simulating black hole feeding, which is oddly appropriate considering black holes themselves consume enormous amounts of matter. Everyone involved appears committed to excessive intake, yet despite all this complexity, one conclusion keeps resurfacing. The early universe may genuinely have allowed black holes to grow far faster than previously assumed. Not infinitely fast, not magically, but faster. Enough faster that billion solar mass quasars become difficult rather than impossible, and that distinction matters enormously. Because once something becomes merely difficult, the universe usually finds ways to accomplish it anyway. Nature is remarkably patient when given millions of years and absurd quantities of hydrogen. There is also growing evidence that early galaxies may have been especially efficient at delivering gas inward. Modern galaxies often possess relatively stable rotational structures. Gas orbits calmly for long periods. Young galaxies were far less organized. Collisions disrupted stability constantly. Streams of cold gas flowed through dark matter halos directly into galactic centers. Dense filaments connected structures across enormous scales. The whole early cosmos functioned almost like a giant gravitational plumbing system, channeling matter inward wherever gravity demanded it. Under such conditions, black holes may have experienced feeding environments unlike anything common today, and perhaps that is the deeper lesson hidden inside J0313-1806. Maybe we unconsciously imagine the early universe as primitive because it was young. But young does not necessarily mean slow. The infant cosmos was dense, energetic, and extremely active. Gravity operated efficiently. Gas was abundant. Structures collided constantly. In some respects, the first billion years after the Big Bang may have represented one of the most productive eras in cosmic history. Stars formed rapidly. Galaxies assembled rapidly. Black holes grew rapidly. Everything happened at astonishing speed. There is something strangely fitting about that. The universe itself began in violence and expansion. Perhaps it spent its youth experimenting aggressively with extreme structures before settling gradually into the calmer modern cosmos we observe today. Still, even with super Eddington accretion and efficient gas inflows, J0313-1806 pushes models close to their limits. Researchers continue debating whether ordinary stellar seeds plus rapid feeding truly suffice. Some think yes, barely. Others remain unconvinced, which is why attention increasingly turns toward another possibility entirely. What if the original seeds were already enormous from birth? Because if black holes in the early universe began life vastly larger than ordinary stellar remnants, then the feeding problem becomes much easier to solve. You no longer need impossible growth from tiny beginnings. Instead, the universe starts with giant foundations almost immediately. The first stars in the universe were born into a cosmos that barely resembled the one we know today. There were no rocky planets yet, no oxygen-rich atmospheres, no carbon forests, no galaxies with elegant spiral arms drifting quietly through space. The universe was simpler then, at least chemically speaking. Almost everything consisted of hydrogen and helium, the lightest elements forged during the first few minutes after the Big Bang. And strangely enough, that simplicity may have allowed the earlier stars to become enormous, far larger than most stars alive today, possibly large enough to help explain how impossible black holes like J0313-1806 appeared so quickly. 2. Understand why astronomers suspect the first stars were giants, we need to think about how stars form in the first place. Modern stars emerge from cold molecular clouds. Gravity slowly pulls gas inward, regions collapse, fragment, and eventually ignite fusion. But cooling is essential to this process. When gas clouds cool efficiently, pressure drops. Lower pressure allows gravity to compress material more easily. The cloud fragments into smaller clumps, each potentially becoming an individual star. Heavy elements play a major role in cooling. Carbon, oxygen, silicon, iron, and other elements radiate energy away efficiently. Dust grains also help dissipate heat. Modern galaxies contain abundant heavy elements because countless generations of stars have enriched interstellar space through supernova explosions. The early universe had none of that. No previous stars had existed yet. No stellar furnaces had manufactured heavier elements. No ancient supernovae had seeded galaxies with cosmic debris. The primordial universe was chemically primitive, and that changes everything. Without efficient cooling, giant gas clouds struggled to fragment into many small stars. Instead, gravity may have gathered huge quantities of matter into fewer, much larger objects. This is one reason astronomers believe the first generation of stars, called Population 3 stars, may have been extraordinarily massive, possibly hundreds of times heavier than our Sun. Some theoretical models even allow stars exceeding 1,000 solar masses under extreme conditions. Now, to be fair, astronomers have not directly observed a true Population 3 star yet. These objects lived far too early and likely died very quickly. But simulations consistently suggest primordial stars behave differently from modern ones, and the differences could have been dramatic. Imagine looking up into a sky containing stars unlike anything commonly seen today. Blindingly bright, extremely hot, immensely massive, living fast and dying violently. The first stars may have been cosmic overachievers in the most dangerous possible sense. Massive stars consume fuel at astonishing rates. Gravity squeezes their cores harder, which raises temperatures, which accelerates fusion enormously. A star 10 times more massive than the Sun does not merely shine 10 times brighter, it can burn vastly more intensely. As a result, these giant primordial stars probably lived only a few million years before collapsing. Compared to our Sun's projected lifetime of roughly 10 billion years, that is astonishingly brief. The first stars may have spent cosmic history sprinting directly toward catastrophe. And catastrophe is exactly where black holes enter the story. When massive stars exhaust their fuel, gravity wins. The core collapses inward violently. Depending on the star's mass, the result may be a neutron star or black hole. But extremely massive primordial stars could have produced unusually large black hole remnants from the very beginning. Instead of forming tiny stellar black holes containing only a few solar masses, Population 3 stars may have left behind seeds dozens or hundreds of times heavier. This matters tremendously, because every additional solar mass in the initial seed reduces the amount of subsequent growth required to reach supermassive scales. Starting with a black hole of 300 solar masses is much easier than starting with one containing only 10. The cosmic clock problem becomes less severe, not solved completely, but less severe. And yet even here, complications appear, because the most massive stars may not always produce black holes at all. Some giant stars undergo something called pair instability supernovae. This is one of those wonderfully terrifying astrophysical processes where nature decides ordinary explosions are insufficiently dramatic. Inside extremely massive stars, temperatures can become so high that energetic gamma rays spontaneously transform into electron-positron pairs. That conversion reduces radiation pressure supporting the star against gravity. The core suddenly destabilizes, collapse begins rapidly, then runaway fusion ignites explosively. The entire star can detonate completely, leaving no black hole behind whatsoever, no remnant, no neutron star, nothing, just enormous explosions scattering heavy elements into space. Essentially, the star self-destructs so thoroughly that even gravity fails to salvage a black hole afterward. This creates an interesting mass gap. Certain ranges of stellar masses may avoid black hole formation because pair instability destroys the star entirely. Even the universe apparently has situations where things become too unstable to collapse properly. Still, sufficiently massive stars beyond that range could collapse directly into black holes again, and these giant primordial stars remain attractive candidates for producing the earliest massive seeds. There is another fascinating aspect to population 3 stars as well. They likely transform the entire universe around them. Remember the cosmic dark ages we discussed earlier, the long period after a combination when the universe contained mostly neutral hydrogen and no stars yet existed. The first stars ended that darkness. Their intense ultraviolet radiation kinized surrounding hydrogen gas. Light spread through the cosmos for the first time. Astronomers call this process reionization. The first stars effectively turned the lights back on across the universe, and they probably did so violently. Population 3 stars may have emitted enormous radiation fields. Their death seeded space with the first heavy elements. Their explosions reshaped nearby gas clouds. The earliest galaxies evolved under their influence. In many ways, these primordial stars became the architects of everything that followed, which means they may also have prepared environments favourable for rapid black hole growth. Massive stars produce massive remnants. Massive remnants produce stronger gravity. Stronger gravity attracts more gas. More gas means faster growth. The process can accelerate surprisingly quickly under the right conditions, especially in the dense, chaotic early universe. Still, astronomers face a difficult balancing act here. Even enormous stellar remnants struggle to explain J0313-1806 completely. Suppose the first stars produced black hole seeds around several hundred solar masses. Helpful, certainly, but growing from hundreds to 1.6 billion solar masses within roughly 670 million years still demands extraordinary feeding efficiency. The black hole would need to consume matter aggressively almost continuously, and as we discussed earlier, black holes are limited by radiation pressure and feedback effects. The timeline remains tight, very tight. Some researchers therefore propose that primordial stars may have formed inside dense stellar clusters where repeated mergers occurred. Perhaps giant stars collided and combined before collapsing. Perhaps black holes themselves merged repeatedly inside crowded early environments. Maybe the first galaxies acted like cosmic traffic jams, where gravity constantly pushed massive objects together. Mergers offer another path toward rapid growth. After all, black holes do not need to eat only gas. They can also merge with one another. When two black holes spiral together and collide, they form a larger black hole while releasing enormous gravitational waves across space-time. The early universe, packed densely with forming structures, may have hosted such events frequently. But mergers alone probably cannot solve the entire puzzle either. They help. Everything helps a little. Yet J0313-1806 remains stubbornly enormous. That is part of what makes it so compelling scientifically. Every proposed explanation appears plausible individually, but incomplete alone. Massive primordial stars help. Super Eddington feeding helps. Frequent mergers help. dense early galaxies help. But the black hole still sits near the edge of what these mechanisms comfortably produce, and perhaps that is exactly what the universe intended. Nature rarely organizes itself around human convenience. Sometimes the cosmos creates objects specifically designed to force better theories into existence. There is something strangely poetic about that process without needing to become overly poetic about it. Scientists spend decades refining models, then ancient light arrives from across the observable universe, carrying evidence that something happened faster, larger, or earlier than expected. Back to the equations everyone goes. The study of populations. 3 stars has become increasingly important because these objects may hold answers not only about black holes, but about the origins of cosmic structure altogether. The first stars changed everything. They produced the first heavy elements. They altered surrounding gas chemistry. They affected galaxy formation. They influenced reionization. And perhaps most importantly for our story tonight, they may have created the earliest black hole seeds from which monsters eventually grew. Researchers continue searching for observational evidence of these ancient stars. Direct detection remains difficult because population 3 stars existed extremely early and lived briefly. But astronomers hunt for indirect clues constantly. Chemical signatures inside ancient stars, patterns of heavy element abundances, infrared observations of primordial galaxies, supernova fingerprints preserved across cosmic history. The James Webb Space Telescope has become especially important in this effort. Webb can observe extremely distant galaxies from the era when population 3 stars likely existed. Scientists hope these observations may eventually reveal environments shaped by the first stellar generation. Already Webb has found galaxies appearing surprisingly mature at unexpectedly early times, which admittedly seems to be becoming a recurring theme in modern cosmology. Everything in the early universe increasingly appears more productive than anticipated. Bigger galaxies, earlier structures, faster growth, ancient black holes behaving like cosmic speedrunners. At some point, astronomers began wondering whether the first stars themselves were also more extreme than earlier theories predicted. Maybe primordial conditions naturally favoured gigantic stellar masses. Perhaps the universe's first attempt at star formation produced enormous luminous beasts unlike the relatively modest stars common today. If so, then giant primordial stars may have laid the groundwork for supermassive black holes astonishingly quickly. There is another subtle point worth noticing here. The modern universe is actually harder for giant stars to form in some ways. Heavy elements cool gas efficiently, promoting fragmentation into smaller stars. The chemically primitive early universe may therefore have favoured larger average stellar masses naturally. In other words, the first stars may not have been unusually giant despite primordial conditions. They may have been giant because of primordial conditions. The infant cosmos operated under different physical environments than modern galaxies, and under those conditions, gravity may have built structures differently. This possibility helps explain why astronomers treat the early universe almost as a separate astrophysical ecosystem. You cannot simply assume today's processes operated identically billions of years ago. Different chemistry, different densities, different radiation backgrounds, different galactic environments, everything changes. And somewhere inside that rapidly evolving primordial cosmos, the ancestors of J0313-1806 may have begun forming almost immediately after the first stars ignited. Perhaps giant population 3 stars collapsed into unusually massive black hole seeds. Perhaps those seeds entered dense feeding environments inside young galaxies. Perhaps mergers accelerated their growth further. One mechanism layered atop another, the universe building complexity rapidly through overlapping processes. Still, some scientists remain unconvinced that even giant primordial stars fully solve the problem, because ultimately there may still not be enough time. For most of modern astronomy, stars came first. That seemed perfectly reasonable. Stars are everywhere. Galaxies glow because of them. Heavy elements come from them. Planets form around them. Life itself depends on the chemistry they create. Naturally, astronomers assumed black holes began as stellar corpses. A massive star lives briefly, collapses violently, and leaves behind a black hole remnant. Simple, elegant, comfortingly familiar. But J0313-1806 and other ancient quasars forced researchers to consider a much stranger possibility. What if some black holes never needed stars at all? What if, under the extreme conditions of the early universe, enormous gas clouds collapsed directly into giant black holes from the beginning? No stellar phase, no supernova, no ordinary life cycle, just gravity bypassing the usual process entirely and creating a monster almost immediately. This idea is known as direct collapse, and while it sounds slightly like the title of a very expensive disaster movie, it has become one of the leading explanations for how supermassive black holes appeared so early in cosmic history. To understand why direct collapse matters, we first need to think carefully about the ordinary path again. Suppose you begin with a massive primordial star. Perhaps it leaves behind a black hole containing 100 solar masses. Helpful, certainly. But growing from 100 solar masses to 1.6 billion within only 670 million years still requires extraordinary feeding conditions nearly all the time. The black hole must eat continuously, aggressively, efficiently. Any long interruptions become problematic. The cosmic clock remains painfully tight. Now imagine instead that your starting seed already contains 100,000 solar masses. Suddenly everything changes. The growth problem becomes dramatically easier. You no longer need miraculous feeding histories stretching continuously across the early universe. You simply begin much larger. And that is the core attraction of direct collapse models. Rather than starting small and growing painfully fast, the universe may occasionally have built enormous black hole seeds almost immediately. Of course, achieving that is not simple either. Gas clouds do not normally collapse directly into giant black holes because they tend to fragment. As gravity compresses a cloud, the gas heats up. Under ordinary circumstances, cooling processes allow smaller dense regions to form inside the cloud. Those regions become stars. Instead of one enormous object, you get many smaller ones. Modern galaxies do this constantly. A giant molecular cloud collapses and fragments into clusters filled with stars of different sizes. Gravity rarely gets the chance to dump all the mass into one single object. The cloud breaks apart first. So direct collapse requires preventing fragmentation. And this is where the early universe may have provided unusual opportunities. Remember, primordial gas contained almost no heavy elements. Cooling mechanisms were weaker than in modern galaxies. That already helped favour larger structures, but additional conditions were likely necessary. One crucial factor may have been intense ultraviolet radiation from nearby star-forming regions. At first glance, radiation sounds like it should make collapse harder. Often it does. But certain ultraviolet wavelengths specifically destroy molecular hydrogen, which is one of the main cooling agents in primordial gas clouds. Without molecular hydrogen, gas remains hotter. Hotter gas resists fragmentation, and if fragmentation is suppressed long enough, an enormous gas cloud may continue collapsing inward as one giant structure instead of breaking into stars. Essentially, nearby radiation sterilizes the cloud's ability to cool efficiently. That sounds unpleasant, but astrophysically speaking, it may have been extremely useful. Imagine trying to freeze water into many small ice cubes. Efficient cooling helps tiny structures form. Now imagine keeping everything warm enough that the water remains fluid and collapses inward together instead. That is roughly the kind of balancing act direct collapse requires. Under the right conditions, gravity may overwhelm everything before ordinary stars have time to appear. The result could be a supermassive object, sometimes called a supermassive star or quasi-star. These hypothetical objects would be utterly unlike ordinary stars. Some models suggest masses reaching hundreds of thousands of solar masses. Their interiors would become unstable rapidly. eventually collapse would occur directly into a giant black hole seed, and importantly, that seed begins enormous from birth. Suddenly the timeline problem surrounding J0313-1806 becomes much less terrifying. A 100,000 solar mass seed feeding steadily can plausibly reach billions within several 100 million years. Still difficult, but plausible. Which is why direct collapse models became increasingly popular among researchers trying to explain ancient quasars. There is something wonderfully unsettling about the whole idea. For most of cosmic history, stars appear as the universe's primary builders. They create structure, they forge elements, they shape galaxies. Yet direct collapse suggests that in some rare regions, gravity may have skipped the stellar middleman entirely. The cosmos simply gathered enormous clouds and dropped them directly into black holes. No proper stars required. Nature occasionally prefers shortcuts. Of course, astronomers immediately encountered another challenge. How often could this actually happen? Because direct collapse requires fairly specific environments, you need large primordial gas clouds, strong ultraviolet radiation nearby, limited heavy elements, appropriate gas dynamics, low fragmentation rates. The conditions become somewhat delicate. Not impossible, but probably uncommon. Then again, the observable universe contains hundreds of billions of galaxies. Even rare processes become inevitable somewhere given enough cosmic real estate, and the early universe may have been especially favourable for unusual structures. Galaxies were densely packed. Interactions happened frequently. Radiation fields varied dramatically from region to region. The infant cosmos was chaotic enough that extraordinary events may have occurred more often than modern intuition expects. There is another fascinating possibility too. Some researchers think direct collapse black holes may have formed inside dense streams of gas flowing along dark matter filaments. The early universe contained enormous web-like structures shaped largely by dark matter gravity. Ordinary matter followed those gravitational pathways. Where filaments intersected, huge gas reservoirs could accumulate rapidly. Under the right conditions, those intersections may have produced ideal collapse environments, the cosmic web itself helping build giant black hole seeds. That image is strangely beautiful. Invisible dark matter sculpting vast gravitational highways, while primordial gas streams inward toward collapsing monsters hidden inside the first galaxies. Modern cosmology occasionally sounds less like science, and more like someone writing mythology with equations, and yet observations continue supporting the idea that something unusual happened early in cosmic history. Because supermassive black holes appear too early too often, J0313-1806 is not entirely unique. Several ancient quasars now challenge conventional growth models. Direct collapse offers one of the few pathways capable of producing sufficiently large seeds quickly enough. Researchers therefore began searching for indirect evidence. Could any observational signatures distinguish direct collapse black holes from ordinary stellar remnants? Possibly. Some models predict unusual radiation spectra during collapse stages. Others suggest surrounding galaxies may exhibit distinct chemical patterns. The problem is that these events occurred incredibly far away and extremely early. Observing them directly remains difficult. Still, the James Webb Space Telescope has started pushing observations closer to this primordial era than ever before. Webb's infrared sensitivity allows astronomers to study galaxies existing only a few 100 million years after the Big Bang. And already, some observations hint at unexpectedly massive structures appearing remarkably early. Certain galaxies seem brighter or more evolved than traditional models predicted. Potential black hole candidates appear rapidly. Again and again, the young universe looks surprisingly efficient at building complexity. It is important to remain careful here. Astronomers are not claiming direct collapse is proven fact. Far from it. Science advances through evidence, testing, revision, and skepticism. But direct collapse has moved from speculative curiosity towards serious theoretical consideration, because observations increasingly demand mechanisms capable of rapid black hole formation, and direct collapse solves several problems simultaneously. Large seeds reduce growth requirements. Early formation fits cosmic timelines better. Dense primordial environments make the process plausible. No single explanation fully resolves every difficulty, but direct collapse helps considerably. There is another deeply interesting implication as well. If direct collapse occurred, then some supermassive black holes may actually predate most stars inside their host galaxies. Think about that for a moment. The black hole forms first, then galaxies assemble around it afterward. That reverses the intuitive order many people imagine. Instead of galaxies gradually creating black holes, giant black holes may sometimes have acted like gravitational anchors around which galaxies later organize themselves. Astronomers increasingly suspect black holes and galaxies evolved together from the earliest times. The relationship appears deeply intertwined. Black holes influence star formation through feedback. Galaxies feed black holes through gas inflows. Each shapes the other continuously. But direct collapse hints that black holes may occasionally have taken the lead role from the very beginning. The first giant gravitational structures appearing before mature galaxies even existed. There is something almost eerie about that possibility. The young universe still mostly dark. The first stars only beginning to ignite, and already hidden inside giant collapsing gas clouds, enormous black holes emerging before ordinary galactic structure fully develops, cosmic monsters arriving early enough to shape everything afterward, and once these giant seeds existed, growth could accelerate dramatically. Large black holes exert stronger gravity. Stronger gravity attracts more gas. More gas means more feeding. More feeding means faster growth. The process compounds rapidly, especially inside the dense gas-rich environment of the early universe. J0313-1806 may represent the outcome of exactly such a process. A giant primordial seed born through direct collapse, then fed aggressively for hundreds of millions of years inside one of the universe's earliest massive galaxies. At least that is one of the leading possibilities. And honestly, it remains astonishing no matter how calmly one describes it, because the scales involved are difficult for human intuition to absorb properly. Imagine a gas cloud containing hundreds of thousands or millions of solar masses collapsing across light years of space until gravity compresses the center into a giant black hole. No ordinary star, no gentle intermediate phase, just direct gravitational catastrophe on colossal scales. The universe apparently does not always feel obligated to proceed gradually. Sometimes it builds giant structures almost immediately. That realization has broader consequences beyond black holes alone. It suggests the early universe may have been fundamentally more dynamic and efficient than many older models assumed. Complexity emerged rapidly. Extreme objects formed early. Gravity wasted very little time, and perhaps that should not surprise us too much. After all, the early universe possessed conditions modern galaxies rarely experience: higher densities, abundant pristine gas, frequent mergers, violent radiation fields. Everything existed closer together physically and gravitationally. The infant cosmos may simply have been optimized for rapid structure formation in ways the modern universe no longer is. Still, enormous mysteries remain. How common was direct collapse? What exact conditions triggered it? Did multiple formation pathways operate simultaneously? Could some supermassive black holes come from giant stars while others form directly from gas clouds? Almost certainly, researchers suspect the real universe used several mechanisms together. Nature rarely limits itself to one elegant solution, where many messy ones are available, and black holes, especially ancient ones, continue forcing astronomers toward uncomfortable but fascinating possibilities. Because ultimately, J0313-1806 still sits there in the distant universe waiting patiently inside ancient light. An object that grew too massive too early. A gravitational giant blazing across the cosmos before galaxies had properly matured. If you could somehow travel back to the era of J0313-1806, the universe would not feel ancient. That is one of the strangest parts of this story. From our perspective, the quasar belongs to the unimaginably distant past. Its light has travelled more than 13 billion years to reach Earth. Entire galaxies evolved while those photons crossed expanding space. And yet at the moment that light originally began its journey, the cosmos itself was still remarkably young enough that many modern galaxies did not yet exist in recognisable form, young enough that the Milky Way was still assembling, young enough that heavy elements remained comparatively scarce across much of the universe. The cosmos was still growing up. But despite that youth, the environment around J0313-1806 was anything but quiet. In fact, it may have been one of the most violent places in existence. Modern people often imagine space as calm, silent, empty, peaceful, and to be fair, large regions of space really are extremely quiet. But the early universe surrounding giant quasars was more like an enormous gravitational battlefield. Gas clouds collided constantly. Stars formed at frantic rates, radiation flooded entire regions, galaxies merged repeatedly, black holes fed aggressively, matter moved through space in gigantic streams shaped by invisible dark matter structures. Everything was dense, chaotic, and evolving rapidly. The universe at that time was not settled enough to become graceful. It was still busy becoming, and J0313-1806 sat near the centre of all that turmoil like a gigantic gravitational engine. One of the reasons astronomers care so much about quasars is that they illuminate the environments around them. The black hole itself remains hidden behind the event horizon, but the surrounding activity becomes extraordinarily bright. Gas spiralling inward forms an accretion disk heated to immense temperatures. Radiation pours outward across space. Powerful winds erupt from the system. In some quasars, jets blast matter thousands of light years into surrounding regions. The result is an object so luminous that it can outshine entire galaxies. J0313-1806 was one of those objects. It shined across the early cosmos while feeding near the limits of what black holes can sustain. And because it was so bright, astronomers could examine clues about the galaxy surrounding it. Those clues revealed something remarkable. The host galaxy appeared to be forming stars at extraordinary rates, hundreds of solar masses worth of stars every year. To appreciate how extreme that is, let's compare it to our own galaxy for a moment. The Milky Way forms roughly 1 or 2 solar masses worth of new stars annually today. That is entirely respectable by modern galactic standards. A healthy pace, steady, productive. J0313-1806's host galaxy may have exceeded that by hundreds of times. It was essentially operating like a cosmic furnace, continuously converting enormous gas reservoirs into stars while simultaneously feeding a giant black hole at the centre. Everything in the system seemed to be happening at maximum intensity. And this creates a fascinating contradiction. Black holes require gas to grow. Stars also require gas to form. Both processes compete for the same material. Yet somehow this ancient galaxy supported explosive star formation and rapid black hole feeding simultaneously. The entire environment must have contained staggering amounts of matter. Dense streams of gas likely flowed continuously into the galactic centre. And the young universe was particularly good at delivering such fuel. Remember, galaxies back then were packed much closer together than today. Interactions happened frequently. Mergers were common. Huge filaments of gas connected structures across the cosmic web. Dark matter shaped giant gravitational highways through which ordinary matter flowed. Galaxies did not evolve in isolation. They collided, repeatedly. And galactic collisions are transformative events. When galaxies merge, enormous gravitational disturbances ripple through both systems. Gas clouds compress violently. Star formation surges. Material funnels inward towards central regions. in many cases mergers may dramatically accelerate black hole feeding. The early universe likely experienced these interactions constantly. Young galaxies were still assembling through repeated mergers and accretion events. Some researchers suspect J0313-1806's host galaxy may itself have formed through rapid collisions between multiple proto-galaxies, each merger delivering fresh gas, fresh stars, fresh fuel for the central black hole. The environment would have been extraordinarily unstable, beautiful perhaps from a distance but catastrophically violent up close. There is another important factor too. The radiation from the quasar itself was immense. Quasars do not simply shine gently into surrounding space. Their energy output can reshape entire galaxies. J0313-1806 likely emitted enormous quantities of ultraviolet and X-ray radiation. That energy heated surrounding gas and altered the chemistry of nearby regions. Some observations even suggest the quasar generated extremely powerful outflows, travelling at around 20% the speed of light. Think about that carefully for a moment. Material blasting outward at roughly 60,000 kilometers per second. Not occasional bursts, not isolated explosions, but sustained galactic-scale winds driven by a feeding supermassive black hole. These outflows matter enormously because they influence the future evolution of galaxies. Gas expelled from central regions can no longer form stars efficiently. Star formation slows, galactic growth changes. Modern astrophysics increasingly views black holes not as passive objects, but as regulators shaping entire galaxies through feedback, and J0313-1806 may represent feedback operating near maximum intensity. The black hole feeds, radiation increases, outflows strengthen, surrounding gas heats or escapes, the environment transforms, yet somehow the system continued supplying enough material to sustain both the quasar and intense stellar birth simultaneously. That implies enormous gas reserves, possibly among the richest environments in the young universe. In a sense, giant quasars like J0313-1806 behave almost like cosmic storms. They disrupt everything nearby, heat surrounding matter, generate turbulence, launch high-speed winds, illuminate space across billions of light years. And all of this while sitting inside galaxies still struggling to assemble themselves properly. There is something wonderfully excessive about the entire process. The early universe did not merely create black holes, it created hyperactive ecosystems around them, and these environments may have played crucial roles in shaping the future cosmos. Because the energy released by quasars affects much more than their immediate surroundings. Ultraviolet radiation escaping into intergalactic space contributes to cosmic reionization, the long process through which the neutral hydrogen filling the early universe became ionized again after the cosmic dark ages. For hundreds of millions of years after recombination, much of the universe remained filled with neutral hydrogen gas. Then the first stars, galaxies and quasars gradually flooded space with radiation. Hydrogen atoms lost electrons again. The universe became transparent to ultraviolet light. Modern large-scale cosmic structure emerged from this transformation. Quasars like J0313-1806 may have helped drive that process. Their immense luminosity acted like giant beacons piercing through primordial darkness. In fact, one reason astronomers find these ancient quasars so valuable is precisely because they illuminate conditions during the reionization era. Light travelling from the quasar passes through intergalactic hydrogen on its journey toward Earth. By studying absorption patterns in that light, researchers learn about the state of the early universe itself. The quasar becomes both object and flashlight simultaneously, and what that flashlight reveals is a cosmos still in transition, not fully ionized, not fully structured, still evolving rapidly. That transitional quality matters deeply. J0313-1806 existed during one of the most dynamic periods in all cosmic history, The first billion years after the Big Bang saw extraordinary transformation. The first stars appeared, the first galaxies assembled, the first heavy elements spread through space, the first giant black holes emerged. The large-scale architecture of the universe began taking recognizable shape. Everything happened astonishingly fast, and in the middle of all this stood giant quasars blazing across space. There is another fascinating possibility too. Some researchers think quasars may occasionally trigger star formation instead of merely suppressing it. Shock waves from outflows can compress distant gas clouds, potentially initiating new stellar collapse. So black hole feedback might operate both destructively and constructively depending on local conditions. The relationship becomes deeply complicated. Black holes consume matter, but also influence the birth of stars. Stars create heavy elements, but also feed black holes through collapse and gas dynamics. Galaxies organize these processes while being reshaped by them simultaneously. The entire young universe functioned as an interconnected system evolving at incredible speed. And the deeper astronomers look into this era, the more surprising it becomes. For many years, scientists imagined early galaxies as relatively small primitive systems slowly growing toward modern complexity. Instead, observations increasingly reveal galaxies appearing brighter, more massive, and more evolved than expected. Again and again, the infant universe seems strangely mature. J0313-1806 fits that pattern perfectly. Its black hole appears too massive. Its host galaxy appears intensely active. Its environment appears highly evolved despite cosmic youth. Everything about the system suggests rapid structure formation operating near the limits of theoretical expectations. Naturally, this has forced cosmologists to rethink assumptions about early galaxy evolution. Maybe gas inflows were more efficient. Maybe mergers happened faster. Maybe star formation proceeded differently. Maybe black holes and galaxies co-evolved more tightly than earlier models assumed. Or perhaps some important piece of early universe physics remains missing entirely. There is still much uncertainty, and that uncertainty is healthy. Astronomy progresses precisely because observations continue surprising researchers. If the universe behaved exactly as predicted all the time, science would become rather dull. Instead, ancient quasars keep arriving from deep cosmic history, carrying evidence that reality is more complicated, faster, and stranger than expected. J0313-1806 may represent one of the clearest examples of this phenomenon. A black hole too large, too early, too active, living inside a galaxy undergoing extraordinary transformation, while the universe itself remained young. And perhaps most remarkable of all, everything we know about this system comes from ancient light, crossing unimaginable distances through expanding space. Photons emitted more than 13 billion years ago eventually reached tiny instruments built by intelligent creatures orbiting an ordinary star in a fairly average galaxy. There is something deeply humbling about that chain of events, especially because the environment around J0313-1806 no longer exists in the form we observe it. The quasar itself evolved billions of years ago. The galaxy changed, stars aged, structures merged, everything moved forward. What we see today is a preserved moment from the violent youth of the cosmos, a snapshot of one region where gravity, radiation, gas, and time combined to create something extraordinary. If black holes themselves are invisible, quasars are the exact opposite. They are outrageously visible. In fact, quasars are so bright that when astronomers first discovered them in the 1960s, many researchers struggled to believe what they were seeing at all. The observations seemed absurd. Tiny points of light appearing star-like through telescopes, yet somehow emitting more energy than entire galaxies filled with hundreds of billions of stars. It was rather like discovering a flashlight brighter than a continent. Naturally, confusion followed. At first, astronomers did not even know what quasars were. Early observations revealed strange radio sources associated with apparently stellar objects. They looked point-like rather than extended like ordinary galaxies, hence the original name, quasi-stellar radio sources, eventually shortened to quasars because scientists, like everyone else, prefer not saying enormous phrases repeatedly if avoidable. But the real shock came from measuring redshift. Some quasars were incredibly distant, and if they were truly that far away, then their luminosities has to be absolutely colossal. There seemed almost no reasonable physical explanation, until black holes entered the picture. Once astronomers realized that matter falling towards supermassive, black holes could release extraordinary amounts of energy through accretion disks. The puzzle finally started making sense. Quasars, it turned out, were not stars at all. They were feeding supermassive black holes sitting inside galactic centers, and they were among the most powerful objects in the universe. J0313-1806 belongs firmly within this category. Its brightness is one reason astronomers detected it, despite the unimaginable distance involved. Without the quasar surrounding the black hole, the object itself would likely remain hidden from current instruments. The quasar acts like a giant cosmic lighthouse, shining across billions of light years. And honestly, lighthouse may still undersell the situation slightly. Some quasars produce more energy in a single second than our sun emits over thousands of years. That energy comes from gravity, which is one of the most fascinating things about black holes generally. Fusion powers stars, gravity powers quasars. Matter falling inward toward a black hole converts gravitational energy into heat with astonishing efficiency. Gas spiraling through the accretion disk accelerates tremendously. Friction and magnetic turbulence heat the material to extraordinary temperatures, the inner regions of the disk become incandescent. X-rays, ultraviolet radiation, visible light, infrared emissions, all pouring outward simultaneously. And because the black hole itself is relatively compact compared to a galaxy, enormous energy gets concentrated into surprisingly small regions. This is why quasars can outshine galaxies. A supermassive black hole may occupy a volume smaller than our solar system, while producing luminosity greater than hundreds of billions of stars combined. Nature occasionally demonstrates a truly impressive commitment to excess. Now, one of the most important things to understand about quasars is that they are temporary. Galaxies do not remain quasars forever. A quasar phase occurs when enough gas reaches the central black hole rapidly enough to sustain intense feeding. Eventually, fuel supplies decrease or feedback processes disrupt inflows. The quasar dims, the black hole remains, the feeding frenzy ends. In a sense, quasars represent episodes rather than permanent identities, moments when giant black holes become spectacularly active, and in the early universe those moments appear to have happened frequently. That is partly because young galaxies contained abundant gas. Matter had not yet settled into stable, long-lived structures. Galactic collisions and mergers constantly disturbed gas reservoirs, driving material inward towards central regions. The infant cosmos was exceptionally good at feeding black holes, and when black holes feed aggressively, quasars appear. Some astronomers suspect the early universe may have contained many more quasars than we currently observe directly. Not all quasars point conveniently toward Earth. Some may remain hidden behind thick dust clouds. Others may simply be too faint or distant for present instruments to detect. But the ancient cosmos was likely filled with these blazing engines scattered across forming galaxies, giant gravitational furnaces illuminating the darkness. J0313-1806 was one of the brightest known examples from its era, and brightness matters because it tells us about feeding rates. The quasar surrounding J0313-1806 shines so intensely that astronomers estimate the black hole was consuming enormous amounts of matter continuously. Near the Eddington limit, possibly beyond it at times, this was not a starving black hole patiently nibbling gas over billions of years. This was a gravitational monster actively devouring its environment, while blasting radiation across space. And that radiation changes everything nearby. Quasars are not passive light bulbs, they shape galaxies. Powerful winds erupt outward from accretion disks. Radiation heats surrounding gas. Jets may launch particles enormous distances through intergalactic space. Modern galaxy evolution theories increasingly treat quasars as regulators, influencing star formation and galactic structure itself. In some galaxies, quasar feedback may shut down future star formation by expelling or heating gas reservoirs. In others, shockwaves may compress distant gas clouds and trigger stellar birth. The relationship becomes complicated quickly. Quasars both create and destroy possibilities simultaneously. There is something almost ecological about it. Matter flows inward, energy flows outward, galaxies respond, structures evolve, the black hole and galaxy continuously influence one another. And during the early universe, those interactions may have been especially intense. Young galaxies were dense and chaotic. Gas moved rapidly through cosmic filaments shaped by dark matter. Collisions disrupted stability constantly. The conditions favoured giant feeding events, and giant feeding events favoured quasars. One fascinating aspect of quasars is how efficiently they produce energy compared to stars. Nuclear fusion inside stars converts only a small fraction of mass into energy. Accretion onto black holes can be much more efficient. As matter spirals inward, enormous gravitational energy gets released before crossing the event horizon. In fact, accretion onto supermassive black holes ranks among the most efficient energy generation processes known in the universe, which means quasars achieve ridiculous brightness without requiring ridiculous amounts of mass consumption compared to stellar processes. Gravity itself becomes the engine. There is another reason quasars matter profoundly to astronomy. Because they are so bright, they allow scientists to probe regions of the universe otherwise inaccessible. Light from distant quasars passes through enormous stretches of intergalactic space before reaching Earth. Along the way, intervening gas clouds absorb specific wavelengths. Astronomers study these absorption signatures carefully. Each one contains information about the matter between us and the quasar: composition, temperature, ionization state, motion, distribution. In this sense, quasars act almost like giant backlights illuminating the structure of the universe itself. Without quasars, much of the early cosmos would remain far more difficult to study. J0313-1806 therefore serves two roles simultaneously. It is both an astrophysical mystery and a tool for observing the young universe. Its ancient light carries information not only about the black hole, but about the cosmic environment surrounding it. And that environment appears extraordinarily dynamic. The quasar existed during the era of reionization, when ultraviolet radiation from the first stars and quasars gradually transformed neutral hydrogen throughout the universe. Before reionization, much of space remained filled with neutral gas. Afterward, the universe became transparent to ultraviolet light. This transition represents one of the major milestones in cosmic history. Quasars likely contributed significantly to it, especially giant luminous quasars capable of flooding surrounding regions with radiation. There is something strangely dramatic about imagining the early universe slowly lighting up for the first time. For hundreds of millions of years after a combination, darkness dominated. Then stars ignited, galaxies formed, quasars erupted. Gradually the cosmos transformed into something recognizable, and giant black holes participated in that transformation from surprisingly early times. This realization has changed how astronomers think about supermassive black holes altogether. For decades, black holes were often viewed almost as secondary galactic features. Interesting certainly, but not central. Now evidence increasingly suggests they were major participants in cosmic evolution from the very beginning. Quasars influenced galaxy growth, affected star formation, contributed to reionization, redistributed energy across enormous scales, perhaps even shape the architecture of large cosmic structures indirectly. And because quasars are so luminous, astronomers can observe them at extraordinary distances. Some of the farthest known objects in the universe are quasars precisely because their brightness makes them detectable across billions of light years. In effect, quasars become time machines. When researchers observe ancient quasars, they see the universe as it existed near the beginning of cosmic history, not reconstructed, not simulated, actually observed. The photons arriving today left their sources before Earth existed. There is something almost impossible feeling about that. Ancient light, travelling uninterrupted across expanding space for over 13 billion years, until finally colliding with telescope mirrors on a small rocky planet around an ordinary star. And inside that light, evidence of giant feeding black holes already operating near full intensity. J0313-1806 stands out even among quasars because of its timing. Its brightness alone would already make it remarkable. Its mass alone would already raise questions. But combining both properties at such an early cosmic epoch transforms the object into something deeply challenging. The quasar essentially announces that enormous black holes existed, while the universe itself remained young. That realization forces astronomers toward difficult conclusions. Either black hole formation happened extremely efficiently, or giant seeds formed early, or feeding rates exceeded conventional expectations, possibly all at once. The universe, once again, appears unwilling to choose the least dramatic option. There's also something wonderfully ironic about quasars philosophically. Black holes are famous for trapping light, yet the brightest sustained objects in the universe are often powered by black holes themselves. The darkness creates brilliance, gravity generates illumination. The regions closest to invisibility become among the most luminous places in existence. Astrophysics occasionally feels strangely poetic, even when one tries very hard not to sound poetic about it. Of course, quasars eventually fade. Fuel runs low, accretion slows, radiation decreases, the galaxy evolves onward. Most supermassive black holes in the modern universe are comparatively quiet. Sagittarius A star, the black hole at the centre of the Milky Way, currently feeds only modestly. Our galaxy is not a quasar, thankfully. A quasar-level black hole at the centre of the Milky Way would make the night sky considerably more stressful. But billions of years ago, many galaxies likely experienced active quasar phases during their violent youth. J0313-1806 represents one such phase preserved in ancient light. A glimpse into an era when galaxies and black holes evolved rapidly together. And the more astronomers study these ancient quasars, the clearer it becomes that supermassive black holes were not merely passive passengers inside galaxies. They may have helped shape the earliest galaxies from the very beginning, which raises an even larger question. If giant black holes and quasars existed so early, then how much of the modern universe was built under their influence? For a very long time, astronomers imagined the first galaxies as relatively small and fairly simple places. That assumption made intuitive sense. After all, the early universe had only recently begun forming stars. Matter was still organizing itself after the Big Bang. Heavy elements remained rare. Large structures should, in theory, require time to assemble, so researchers pictured young galaxies as modest systems gradually growing larger through mergers and slow accumulation. Small beginnings leading eventually to mature galaxies like the Milky Way. Then objects like J0313-1806 complicated everything. Because giant quasars do not emerge inside tiny sleepy galaxies. To produce a black hole feeding at extraordinary rates, the surrounding galaxy must already possess enormous reservoirs of gas, active star formation, and complex gravitational structure. In other words, if J0313-1806 existed, then at least some galaxies in the young universe must have matured astonishingly quickly. The black hole itself became evidence that early galaxies were far more active and sophisticated than older models comfortably predicted. and this realization has gradually transformed how astronomers think about the first billion years of cosmic history. One of the key ideas in modern cosmology is hierarchical structure formation. Small structures form first, then they merge into larger ones. Tiny dark matter halos attract gas. Small galaxies emerge. Those galaxies collide and combine repeatedly over time. Eventually, large galaxies appear. This basic framework remains extremely successful overall. But J0313-1806 suggests parts of the process may have unfolded with startling speed. Because growing a billion solar mass black hole requires an environment capable of sustaining intense feeding over long periods, that means large gas inflows, dense galactic structure, rapid star formation, strong gravitational organization. The host galaxy surrounding J0313-1806 was not primitive in any ordinary sense. It was already functioning like a major galactic system while the universe itself remained remarkably young, and increasingly, astronomers are finding similar evidence elsewhere. The deeper telescopes look into the early universe, the more galaxies appear unexpectedly evolved. Some are brighter than anticipated. Some contain surprisingly mature stellar populations. Some seem larger or more massive than standard models initially predicted for such early times. The infant cosmos keeps looking strangely productive, almost impatient. The James Webb Space Telescope has amplified this tension dramatically. Webb was designed specifically to observe the early universe in infrared wavelengths, where ancient stretched light becomes visible after travelling billions of years through expanding space. And almost immediately after beginning operations, Webb started revealing galaxies appearing earlier, brighter, and more developed than many astronomers expected. Now, it is important not to overreact. The universe is not breaking cosmology, despite what enthusiastic headlines occasionally suggest. But observations are forcing refinement. The early universe may have built structures more rapidly and efficiently than older simulations predicted. J0313-1806 fits directly into that emerging picture. Because giant black holes and mature galaxies appear deeply connected. In modern galaxies, astronomers observe strong correlations between central black hole mass and galactic properties. Larger galactic bulges often host larger supermassive black holes. The relationship is remarkably consistent. This suggests galaxies and black holes evolved together somehow, not independently, not accidentally, together. And if that relationship already existed only a few 100 million years after the Big Bang, then galaxy evolution began organizing itself astonishingly early. One possibility is that rapid gas inflows fed both star formation and black hole growth simultaneously. Young galaxies in the early universe likely accreted huge amounts of cold gas from surrounding cosmic filaments. That gas provided raw material for stars while also funneling inward towards central black holes. Essentially, the galaxy and black hole may have been growing in parallel. The same fuel source feeding both systems. That sounds straightforward enough until you remember the scales involved. J0313-1806's host galaxy may have formed stars hundreds of times faster than the Milky Way currently does. The central black hole simultaneously consumed matter near theoretical feeding limits. The entire galaxy operated like an enormous gravitational machine processing gas at extraordinary rates. And all this happened while the universe was still in cosmic childhood. There is something deeply strange about that pace. Human intuition tends to associate youth with simplicity. Young forests contain saplings. Young civilizations possess limited infrastructure. Young stars are smaller. Young galaxies, however, may not always behave modestly. Under primordial conditions, growth could proceed with surprising aggression, partly because the early universe contained enormous amounts of available gas. Stars had not yet locked much matter into long-lived stable systems. Galaxies collided constantly. Dark matter structures concentrated material efficiently. The cosmos itself was denser back then. everything existed physically closer together. That density accelerated interactions. Imagine trying to grow cities in a world where every resource, river and transportation route lies packed closely together. Development happens faster simply because everything needed already sits nearby. The early universe functioned somewhat similarly. Gas streams fed galaxies continuously. Mergers disrupted stable motion and drove matter inward. Star formation surged. Black holes fed. Complexity emerged rapidly. There is another important implication hidden here as well. If galaxies evolved this quickly, then the first generation of stars must also have enriched the universe with heavy elements surprisingly early. Remember, the Big Bang produced mostly hydrogen and helium. Everything heavier formed later inside stars and supernovae. Yet observations of early quasars often reveal surprisingly enriched environments. That means multiple generations of stars had already formed and died by the time objects like J0313-1806 appeared. The cosmic timeline becomes crowded quickly. First stars ignite. They evolve and explode. Heavy elements spread. Galaxies grow. Black holes feed. Quasars emerge, all within only a few 100 million years. The early universe was not waiting around politely. It was busy. Extremely busy. This has led some astronomers to rethink assumptions about star formation efficiency in primordial galaxies. Perhaps the first galaxies converted gas into stars much faster than modern galaxies typically do. Or maybe early gas dynamics allowed giant starbursts to occur frequently. Possibly black hole feedback itself influenced galactic evolution more strongly than previously realized. Again, the picture becomes increasingly interconnected. Nothing evolves in isolation. Black holes shape galaxies. Galaxies feed black holes. Stars enrich gas. Gas drives new star formation. Radiation alters chemistry. Dark matter sculpts gravitational structure underneath everything. The first galaxies may therefore have resembled ecosystems more than static objects. Chaotic, evolving systems where every component affected the others continuously. And J0313-1806 may represent one of the most extreme examples ever observed. There is also a fascinating question about galactic architecture here. Modern galaxies often display organized shapes, spiral arms, central bulges, stable rotational dynamics. The first galaxies were likely much messier, clumpy, turbulent, irregular, gas-rich systems colliding and reorganizing constantly. Yet despite that apparent chaos, they still managed to produce giant black holes rapidly. That suggests order can emerge surprisingly quickly, even inside violent environments. Gravity is very good at organizing matter eventually, especially when enough mass accumulates. Some simulations now suggest that cold gas streams flowing along dark matter filaments may have delivered matter directly into galactic centers efficiently enough to sustain rapid black hole growth. Instead of relying solely on random mergers, galaxies may have possessed relatively stable supply lines, feeding central regions continuously. The cosmic web itself acting almost like an enormous infrastructure network. Again, dark matter appears quietly essential here. Even though we still do not know what dark matter actually is, its gravitational influence shaped the scaffolding upon which galaxies formed. Without dark matter, ordinary matter alone likely could not have assembled large structures quickly enough. In a sense, invisible matter helped build the visible universe. And inside some of those dark matter halos, galaxies like the host of J0313-1806 emerged astonishingly early. One particularly intriguing possibility is that supermassive black holes may actually have helped stabilize early galaxies. Large central masses influence orbital dynamics significantly. A giant black hole could affect gas flows, star formation regions, and overall galactic structure from the beginning. This reverses older intuition somewhat. Instead of galaxies gradually producing black holes as secondary features, Giant black holes may have acted as foundational components, helping organize young galaxies around themselves. The relationship becomes almost symbiotic, and that possibility matters because it changes the story of cosmic evolution fundamentally. Black holes stop being late-stage curiosities. They become central participants from the start. Modern astronomy increasingly treats supermassive black holes not merely as endpoints of stellar collapse, but as major drivers of galactic evolution across cosmic time. J0313-1806 strengthens that perspective enormously. Because if giant black holes existed this early, then they influenced galaxy formation almost immediately after the first structures emerged. There is something wonderfully unsettling about that realization. The universe barely exits its dark ages, and already giant feeding black holes are reshaping galaxies. Cosmic history escalates quickly. Another clue comes from quasar feedback itself. The enormous energy emitted by quasars affects surrounding gas dramatically. Outflows can suppress star formation by heating or ejecting material, but under certain conditions, shockwaves may also compress gas and trigger new stellar birth. This means quasars may both regulate and stimulate galaxy growth depending on circumstances. The first galaxies therefore evolved under intense influence from central black holes. Some regions may have been sterilized, others energized. The galaxy becomes a dynamic battlefield between gravity, radiation, cooling, and turbulence. And somehow, from all that violence emerged the long-term structures that eventually produced galaxies like our own. There is another subtle but important lesson hidden inside all this. The universe achieved complexity remarkably early. Not life, of course. That would come vastly later. But structural complexity, galaxies, black holes, chemical enrichment, feedback systems, large-scale organization, all appearing within a relatively short period after the Big Bang. Sometimes human beings unconsciously imagine the universe spending billions of years drifting quietly before interesting things happen. In reality, interesting things began happening almost immediately. Gravity wasted very little time. And perhaps that should not surprise us too much. The universe began with enormous energy and dense matter distributions. Under those conditions, collapse and structure formation proceeded naturally. The first galaxies were not miniature practice versions of later systems. They were active participants in rapid cosmic evolution. Messy, violent, luminous participants. And J0313-1806 provides one of the clearest windows into that era. A giant black hole surrounded by a galaxy evolving furiously, while the universe itself remained young. Ancient light carrying evidence that the first galaxies were not timid beginnings, but highly energetic systems capable of producing some of the largest black holes ever observed. For most of human history, black holes did not exist at all. Not physically, of course. They existed perfectly well in reality. But human beings had no concept of them. Ancient astronomers mapped planets, followed comets, and studied the stars without imagining that invisible gravitational wells lurked inside galaxies, quietly shaping enormous regions of the cosmos. Even after Einstein published general relativity, black holes remained controversial for decades. Many physicists doubted nature would actually permit such bizarre objects to form. The idea sounded too extreme. Regions where gravity becomes so strong that escape itself ceases to exist. Places where space-time curves inward catastrophically. Objects that emit no light while devouring matter around them. It all seems suspiciously dramatic. And yet the universe, once again, demonstrated little concern for human comfort. Black holes turned out to be real. Not only real, but common. And over the past several decades, astronomers have gradually realized something even stranger. Black holes may not merely exist inside galaxies. They may help shape galaxies fundamentally, possibly from the very beginning. Which brings us to one of the largest questions raised by objects like J0313-1806. Did black holes actually help build the universe we live in? Not alone, certainly. Gravity, dark matter, stars, gas dynamics, and cosmic expansion all play enormous roles. But perhaps black holes were not passive passengers in cosmic evolution. Perhaps they were active architects. For a long time, the standard picture seemed straightforward. Galaxies formed first, then stars evolved inside them. Some stars collapsed into black holes. Eventually, black holes grew larger through feeding and mergers. In this version of events, galaxies were primary. Black holes were secondary, interesting, powerful, sometimes alarming, but ultimately byproducts of galactic evolution. Then astronomers began noticing strange correlations. Almost every large galaxy appears to host a supermassive black hole at its centre. And more intriguingly, the mass of that black hole often correlates closely with properties of the surrounding galaxy. Larger galactic bulges tend to contain larger black holes. The relationship is surprisingly consistent. At first, this seemed puzzling. Why should a black hole occupying a comparatively tiny central region know anything about the much larger galaxy surrounding it? The scales differ enormously. A galaxy may span hundreds of thousands of light years. The event horizon of a supermassive black hole remains comparatively tiny, and yet somehow their growth histories appear linked. That connection forced astronomers toward an uncomfortable realization. Black holes and galaxies likely evolved together, continuously influencing one another across cosmic time. And if objects like J0313-1806 existed only a few 100 million years after the Big Bang, then this relationship began astonishingly early, possibly almost immediately after the first galaxies formed. One of the key mechanisms here is feedback, a word that sounds wonderfully harmless considering it involves giant black holes blasting radiation and high-speed particle winds across entire galaxies. When a supermassive black hole feeds aggressively, enormous energy escapes through radiation jets and outflows. That energy affects surrounding gas dramatically. Gas may heat up, it may be pushed outward, it may stop collapsing into new stars, or under some conditions shock waves may compress distant gas clouds and trigger additional star formation instead. Either way, the black hole alters galactic evolution. Modern cosmology increasingly treats this feedback process as essential. Without black hole feedback, many galaxy simulations produce unrealistic results. Galaxies become too massive, star formation continues too efficiently, structures fail to resemble the observed universe properly. Add black hole feedback, and suddenly simulations begin matching reality much more closely, which strongly suggests supermassive black holes are major regulators of galaxy growth. Not minor details, major regulators. And in the early universe, that influence may have been even more important, because young galaxies contained enormous gas reservoirs. Star formation rates were extreme, mergers happened frequently, black holes fed aggressively, quasars blazed across space. The infant cosmos was a far more energetic environment than the modern universe. J0313-1806 existed directly inside this chaotic era. Its black hole was already gigantic. Its host galaxy formed stars at astonishing rates. Powerful outflows erupted from the quasar. Everything about the system suggests intense interaction between black hole and galaxy, which raises a fascinating possibility. Maybe giant black holes did not merely appear inside the first galaxies, maybe they helped organize those galaxies from the beginning. Some researchers now propose that supermassive black holes may actually accelerate galaxy formation under certain conditions. Large central masses influence gas dynamics strongly. They affect orbital structure. They shape gravitational stability. A giant early black hole could help funnel gas inward efficiently, alter star formation patterns, and regulate the growth of surrounding structures. In that sense, black holes become more than consumers. They become organizers, and perhaps the universe we observe today partly emerged under their influence. There is something deeply strange about that idea. Black holes are usually associated with destruction, consumption, collapse. Yet they may also help create long-term order. Galaxies themselves could owe aspects of their structure to giant black holes hidden at their centres, the darkness shaping the light. Astrophysics does occasionally produce concepts that sound suspiciously philosophical, despite everyone involved trying very hard to remain professional. Of course, black holes alone did not build galaxies. Dark matter remains absolutely essential. Invisible dark matter halos provided the gravitational scaffolding necessary for ordinary matter to collapse efficiently after the Big Bang. Without dark matter, galaxies likely could not have formed quickly enough at all. But once galaxies began assembling, supermassive black holes may have become powerful secondary influences, especially in the densest regions, especially during the universe's violent youth, and perhaps especially during quasar phases. Quasars are not subtle objects. A bright quasar can release more energy than entire galaxies combined. Radiation floods interstellar space. Outflows blast matter enormous distances. These effects reshape galactic ecosystems dramatically. Some galaxies may even shut down future star formation almost entirely after powerful quasar episodes expel too much gas. Others may experience triggered starbursts in surrounding regions. The black hole and galaxy effectively enter a long-term feedback loop. Gas feeds the black hole. The black hole alters the gas. The galaxy evolves. New gas flows inward. The cycle continues. Over billions of years, these interactions sculpt cosmic structure gradually. And if giant quasars like J0313-1806 already existed early on, then such feedback cycles may have begun much sooner than astronomers originally imagined. There is another intriguing implication too. If black holes influence galaxy formation from the beginning, then understanding black hole origins becomes central to understanding cosmic history altogether. Not a side topic, a foundational one. This partly explains why discoveries like J0313-1806 generate such excitement among cosmologists. The object is not merely an unusually large black hole, it potentially reveals how the first galaxies evolved, how matter organized itself, how quickly complexity emerged after the Big Bang. The black hole becomes a clue about everything around it, and the deeper astronomers investigate early cosmic history, the more interconnected everything appears. The first stars enriched galaxies chemically. Galaxies fed black holes. Black holes regulated star formation. Radiation transformed intergalactic gas. Dark matter guided structure formation underneath the entire process. Nothing evolved independently. The universe behaves less like a collection of isolated objects and more like an enormous interacting system. That system began organizing itself remarkably quickly, and perhaps that speed is the most surprising aspect of all. Human intuition tends to imagine cosmic evolution unfolding slowly and gently. But the first billion years after the Big Bang were astonishingly productive. Stars ignited, galaxies assembled, heavy elements spread, supermassive black holes appeared, quasars illuminated space. The architecture of the modern universe emerged rapidly. J0313-1806 stands as evidence of that acceleration. A giant black hole already active while the cosmos itself remained young. Some astronomers even wonder whether supermassive black holes influenced the distribution of galaxies on larger scales indirectly. Powerful quasar feedback affects surrounding intergalactic gas. Over time, these effects may alter where future stars and galaxies form. The influence of giant black holes could therefore extend far beyond their host galaxies alone. Though researchers are still investigating such possibilities carefully, there is another reason black holes became increasingly important in cosmology: energy. Black holes are extraordinarily efficient engines. Accretion converts gravitational energy into radiation with remarkable effectiveness. A relatively small amount of infalling mass can produce enormous luminosity. That energy interacts with surrounding matter continuously. In the early universe, When gas densities remained high, those interactions became especially significant. Quasars likely heated huge regions of intergalactic space. They contributed to cosmic reionization. They redistributed matter and energy across vast distances. Again and again, giant black holes appear less like passive objects and more like major participants in cosmic evolution. And this realization changes how we think about galaxies themselves. A galaxy is not merely a collection of stars orbiting quietly. It is a dynamic system shaped by gravity, gas flows, stellar evolution, dark matter, and often a supermassive black hole influencing everything from the center. The Milky Way itself contains Sagittarius, a star, a comparatively calm, supermassive black hole today. But billions of years ago, our own galaxy may also have experienced active quasar phases during its youth. Perhaps every large galaxy passed through similarly violent periods while assembling. If so, then quasars were not rare curiosities in early cosmic history. They were normal stages of galactic adolescence. And the universe we inhabit today emerged from that violent youth. There is something oddly comforting about that in a cosmic sense. The modern universe often appears calm compared to its beginnings. Galaxies drift relatively peacefully now. Star formation has slowed. Quasar activity decreased dramatically over billions of years. The cosmos matured. But hidden inside ancient light from objects like J0313-1806, we can still glimpse those chaotic earlier eras, moments when galaxies were still assembling themselves under the influence of giant feeding black holes, moments when the universe moved faster, burned brighter, and evolved more violently than it does today. And perhaps the greatest lesson from all this is not merely that black holes exist, it is that black holes matter profoundly. They're not just exotic endpoints of collapsed stars. They are woven into the history of galaxies themselves, possibly into the history of cosmic structure altogether. One of the quiet truths of science is that every generation eventually discovers the universe is stranger than it previously believed. This happens repeatedly. Human beings construct careful explanations for reality. The explanations work reasonably well for a while. Predictions succeed, equations behave nicely, confidence grows. Then eventually the cosmos reveals something inconvenient, a planet orbiting unexpectedly, a galaxy moving too quickly, an explosion brighter than anticipated, a black hole too massive too early. And suddenly, scientists find themselves staring at data while muttering phrases like, "Well, that's odd." J0313-1806 belongs very firmly in the "that's odd" category. Because even after all the possible explanations we've explored, giant primordial stars, super Eddington feeding, direct collapse, violent early galaxies, astronomers still face a lingering discomfort. The timelines remain tight. The growth requirements remain extreme. The object still pushes near the boundaries of what many current models comfortably allow. And when observations repeatedly strain theoretical expectations, scientists eventually begin asking a more dangerous question. What if we are missing something fundamental? Not necessarily something dramatic like everything we know is wrong. Science almost never works that way. More often, the broad picture remains correct while some deeper mechanism or hidden process turns out to matter enormously. Newtonian gravity worked beautifully for centuries. Then Einstein revealed it was incomplete. Galaxies behaved strangely. Then dark matter entered the story. The universe expanded. Then astronomers discovered expansion itself is accelerating, leading to dark energy. Again and again, reality turns out more complicated than expected. So when ancient black holes appear uncomfortably early, researchers naturally wonder whether another missing ingredient might exist somewhere in the equations. One possibility involves black hole formation itself. Perhaps nature possesses pathways toward rapid gravitational collapse that current models still underestimate. Direct collapse already pushes in this direction, but maybe the real process is even more efficient under primordial conditions. Maybe early gas dynamics behaved differently. Maybe magnetic fields played larger roles. Maybe radiation transport inside dense collapsing systems operated in ways simulations still struggle to capture fully. The early universe was an extreme environment, and extreme environments often expose gaps in understanding. There is another possibility too. Perhaps black holes in the young universe fed much more aggressively than astronomers once thought possible. Super-Eddington accretion remains an active area of research, precisely because observations increasingly demand rapid growth mechanisms. Maybe the Eddington limit, while important, becomes less restrictive under certain primordial conditions. Dense gas flows might trap radiation more efficiently. Accretion disks may behave differently at extreme feeding rates. Young galaxies may continuously replenish fuel supplies through cosmic filaments. The whole feeding process could operate faster than simplified models initially predicted. But even these explanations sometimes feel only barely sufficient, which is why some researchers cautiously explore even more unconventional possibilities. For example, there are theories involving primordial black holes. These hypothetical objects would not form from stars at all. Instead, they would emerge directly from density fluctuations shortly after the Big Bang itself. In the very early universe, tiny regions slightly denser than their surroundings might collapse gravitationally under extreme conditions. If such primordial black holes formed large enough, they could provide enormous head starts for later growth. This idea remains speculative, very speculative, and there is currently no strong evidence that primordial black holes explain quasars like J0313-1806. But the fact that scientists seriously investigate such possibilities tells you something important. The puzzle is difficult enough that researchers are willing to test ideas far outside older assumptions. Another area of uncertainty involves dark matter itself. Remember, dark matter dominates gravitational structure formation across the universe. Without it, galaxies likely would not exist in anything resembling their observed form, and yet scientists still do not know what dark matter actually is. That remains one of the largest unsolved problems in physics. Most of the matter in the universe is invisible and fundamentally mysterious, which means there is room for surprises. Some theorists wonder whether dark matter might influence black hole formation more directly than standard models assume. Could certain dark matter interactions accelerate collapse? Could unusual dark matter properties create dense early structures more efficiently? Could primordial black hole seeds form inside dark matter concentrations? At the moment, nobody knows. But again, uncertainty itself becomes scientifically valuable. Objects like J0313-1806 force cosmologists to examine assumptions carefully. And whenever assumptions get examined carefully, understanding improves. There is also the uncomfortable possibility that our simulations simply remain incomplete. Modern cosmological simulations are astonishing achievements. Supercomputers model enormous regions of the universe including gravity, gas dynamics, star formation, radiation, dark matter, magnetic fields, and black hole feedback simultaneously. But even the best simulations require approximations. The universe contains almost unimaginable complexity. Tiny physical details sometimes produce enormous long-term consequences. Perhaps current models still underestimate how rapidly structure formation can proceed under primordial conditions. Maybe the early cosmos was simply better at building giant objects than we intuitively expect. And honestly, history suggests caution before declaring anything impossible in astronomy. The universe has a long record of embarrassing confident predictions. For decades, scientists debated whether planets existed around other stars. Now we know of thousands. People once assumed galaxies represented the entire cosmos. Then more galaxies appeared. Neutron stars sounded absurd initially. Black holes sounded absurd. Even the expansion of the universe itself surprised astronomers. Reality repeatedly exceeds imagination. So when researchers describe J0313-1806 as difficult to explain, that does not mean the universe broke physics. It means physics still contains unanswered questions. That distinction matters enormously. Science advances through tension between theory and observation. Observations reveal reality. Theories attempt to explain it. When the two disagree, discovery happens. And ancient quasars currently represent one of the most exciting tensions in cosmology, because the observations increasingly suggest the early universe formed large structures faster than expected. Not infinitely faster, not magically faster, but faster enough to matter. The James Webb Space Telescope has intensified these discussions significantly. Webb continues finding galaxies and structures appearing surprisingly early in cosmic history. Some systems seem brighter, larger, or more chemically evolved than traditional models predicted. Again, none of this destroys cosmology, but it does suggest refinement is needed. The infant universe may have been far more dynamic than older simplified pictures implied, and perhaps that should not surprise us too much. The early cosmos contained extraordinary conditions. Matter existed densely packed together. Gas reservoirs were enormous. Mergers occurred constantly. Radiation fields shifted rapidly. Everything was extreme. Maybe under such conditions, gravity and gas naturally organize complexity very efficiently, or maybe an important ingredient remains hidden. There is another deeply fascinating possibility as well. Perhaps our understanding of black holes themselves remains fundamentally incomplete. This idea becomes especially interesting because black holes already sit at the intersection of two major physical theories that do not fully agree with one another. General relativity describes gravity beautifully on large scales. Quantum mechanics describes microscopic physics with astonishing precision. But near singularities, those theories become deeply uncomfortable together. Inside black holes, our equations effectively break down. Physicists strongly suspect some deeper theory of quantum gravity must eventually replace current incomplete descriptions. And if our understanding of black holes remains incomplete fundamentally, then perhaps early black hole formation also contains surprises not yet recognized. Again, this remains speculative. But speculative ideas become scientifically reasonable precisely when observations refuse easy explanation. J0313-1806 acts almost like a stress test for cosmology. The object pushes models toward their limits and asks whether the underlying assumptions truly hold under extreme conditions. That is valuable. Some of the most important scientific breakthroughs in history emerged because observations failed to match expectations cleanly. Mercury's orbit helped reveal relativity. The ultraviolet catastrophe contributed to quantum mechanics. Galaxy rotation curves revealed dark matter. Perhaps ancient quasars will eventually expose another hidden layer of cosmic physics. Or perhaps they will simply teach us that the early universe was more efficient at building giant structures than older models assumed. Either outcome would be fascinating. There is something wonderfully honest about science at moments like this. Astronomers do not hide the uncertainty. They embrace it, because uncertainty means there are still discoveries waiting, still mysteries unsolved, still truths hidden somewhere inside the cosmos, and objects like J0313-1806 remind us how small our current understanding remains compared to the scale of reality itself. Human beings only recently learned galaxies exist at all. We have studied black holes seriously for less than a century. The observable universe contains hundreds of billions of galaxies, each potentially containing billions of stars and perhaps supermassive black holes of their own. We're still early in the process of understanding the cosmos. Very early. That perspective becomes strangely calming sometimes, especially at night. It is easy to imagine science as a completed encyclopedia of answers. In reality, it resembles an expanding frontier where each new discovery reveals additional unknowns beyond it. J0313-1806 sits directly on that frontier. A black hole from the dawn of cosmic history challenging our timelines, stretching our models, and quietly suggesting the universe may still contain important secrets we have not uncovered yet. And perhaps the most humbling part is this: the object itself does not care whether we understand it. The black hole existed billions of years before Earth formed. Its quasar blazed across the young universe long before life emerged here. The photons reaching our telescopes today began travelling through space before our species existed. Only now, after billions of years, do human beings finally notice them and begin asking questions. Ancient light arriving at a civilization still learning how the universe works. There is something beautiful about that encounter, because every difficult object in astronomy carries the same quiet message. Reality is larger than our current understanding, and somewhere in the darkness beyond familiar knowledge, the universe is still waiting to surprise us again. Tonight we followed ancient light across almost the entire history of the universe. Not metaphorically, literally. Photons that began travelling more than 13 billion years ago eventually arrived here, at Earth, where human beings built machines delicate enough to catch them, and minds curious enough to wonder what they meant. And hidden inside that light was J0313-1806, a black hole so massive and so ancient that it forced astronomers to rethink how quickly the cosmos learned to build enormous things. When we first began tonight's journey, the mystery seemed fairly straightforward. A black hole appeared too early, simple enough. But the deeper we travelled into the young universe, the stranger the situation became, because solving the puzzle of J0313-1806 eventually leads everywhere else. To the first stars, to the first galaxies, to dark matter, to quasar feedback, to cosmic evolution, even to the possibility that our understanding of gravity and black holes themselves may still be incomplete. The object becomes more than a black hole, it becomes a window into the violent youth of the cosmos. And perhaps that is one of the most remarkable things about astronomy generally. The farther outward we look, the farther backward we travel. Every distant object becomes a preserved moment from another era of cosmic history. The night sky is not showing us the universe as it is now. It shows the universe as it was. Light from the moon is already more than a second old when it reaches your eyes. Sunlight is 8 minutes old. The stars above you tonight may be decades, centuries, or thousands of years out of date. And quasars like J0313-1806 belong to an entirely different category altogether. Their light began its journey before Earth existed, before the sun formed, before oceans covered our planet, before life evolved into anything remotely capable of asking questions about black holes. That realization can feel almost impossible to absorb properly. Imagine how much happened while those photons travelled here. Entire galaxies collided and transformed. Stars were born and died by the trillions. Heavy elements spread across the cosmos. Planetary systems formed. Dinosaurs appeared and vanished. Ice ages came and went. Human civilization rose astonishingly quickly in geological terms. And throughout all of it, those ancient photons continued moving steadily through expanding space, never stopping, never turning around, crossing billions upon billions of light years until eventually they encountered telescope mirrors on a small rocky world orbiting an ordinary star in the outer regions of a fairly average galaxy. And from that encounter emerged a mystery, a black hole too large too early, an impossible object from the dawn of cosmic history, quietly informing modern astronomers that the universe may have grown up faster than expected. There is something wonderfully humbling about that chain of events, especially because J0313-1806 itself is long gone in the form we observe tonight. Not gone entirely, of course. The black hole almost certainly still exists somewhere in the distant universe, but the quasar phase we see belongs to the ancient past. The galaxy evolved billions of years ago. Stars formed and died there countless times since. Mergers likely reshaped the system repeatedly. Everything changed. We are witnessing only one frozen moment carried to us through light, Astronomy often works like that. Not observation of the present, but archaeology of space-time itself. And perhaps that perspective changes the way the night sky feels once you truly sit with it for a while. The stars above us stop becoming decorations. They become history, messages, ancient evidence still arriving. Every point of a light represents information crossing enormous distances through time. Even darkness itself contains stories waiting for careful instruments to uncover them. Black holes especially seem to occupy a strange place in human imagination. They are invisible, yet central. Destructive, yet creative. Silent, yet capable of illuminating galaxies through quasars brighter than hundreds of billions of stars combined. And the more scientists study them, the more black holes appear woven deeply into the structure of the universe itself. Not cosmic accidents hiding at galactic centers, fundamental participants in how galaxies evolve, perhaps even in how the first large structures formed after the Big Bang. J0313-1806 helped reveal that possibility. Because the object forced astronomers to confront an uncomfortable truth. The early universe may have been far more efficient, violent, and productive than we once imagined. The first stars may have been giants. The first galaxies may have matured rapidly. Black holes may have formed through exotic collapse pathways. Quasars may have reshaped enormous regions of space while the cosmos was still young. Everything appears to have happened astonishingly fast. And yet somehow, despite all that violence, all that radiation, all those collisions and gravitational catastrophes, the universe eventually produced quiet worlds too. Worlds with oceans, atmospheres, forests, living creatures, eventually conscious creatures capable of understanding that the atoms inside their own bodies were forged inside stars long before Earth existed. That may be the strangest transformation of all. The universe began hot, dense, and almost unimaginably hostile. Now somewhere inside it, a person lies awake listening to a calm voice describing ancient black holes while wrapped in blankets. Cosmic history took a very unexpected turn somewhere along the way. There is another thought worth lingering on for a moment too. J0313-1806 reminds us how incomplete human knowledge still is. Modern science is extraordinarily powerful. We have mapped galaxies, measured cosmic expansion, detected gravitational waves, photographed black hole shadows, and observed light emitted near the beginning of time itself. And still, one ancient quasar can arrive from the distant universe and leave researchers arguing about how it formed. There is something deeply healthy about that. The universe remains larger than our explanations. Mystery still exists. Not because science failed, but because reality is immense. Every discovery opens additional questions beyond it. Every answer reveals deeper unknowns waiting underneath. Objects like J0313-1806 sit at those boundaries, half understood, partly explained, still mysterious enough to keep astronomers awake at night staring at simulations and wondering whether some hidden piece of cosmic history remains undiscovered. And honestly, perhaps that endless unfinished quality is part of what makes astronomy so comforting sometimes. The universe does not become smaller as we learn more about it. It becomes deeper, more layered, more interconnected. Gravity shapes galaxies. Galaxies shape stars. Stars forge elements. Elements form planets. Planets eventually host observers capable of studying black holes born billions of years earlier. Everything links together across staggering scales of time and space, and through all of it, light continues travelling. Ancient light, patient light, light carrying the memory of vanished eras. Tonight, some of that ancient light reached your eyes indirectly through this story. A signal from a time when the universe itself was young. A reminder that enormous mysteries unfolded long before humanity existed and continue unfolding now beyond the limits of what we currently understand. Somewhere out there, beyond the reach of ordinary sight, J0313-1806 still drifts inside the distant universe, its quasar no longer blazing exactly as we see it tonight, its galaxy transformed by billions of additional years of cosmic evolution. And still, the photons from its ancient past continue arriving here, one after another, crossing the darkness patiently. There is something beautiful about that persistence, a universe constantly sending pieces of its history outward in every direction. And perhaps, the next time you look up into the night sky, you'll remember that every star, every galaxy, every faint point of light overhead is part of an ongoing journey through time. Some of those photons began travelling before human civilization existed, some before humanity itself, and somewhere among them are messages from ancient black holes that once illuminated the newborn cosmos, while the first galaxies were still learning how to grow. For now, though, the universe can continue expanding quietly outside your window while you rest here safely on this small and remarkably peaceful planet. Thank you for spending this time with me tonight, and until our next journey through the cosmos together, sleep well.